dash spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue. When in after years we're turning alma mater back to you, may our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're finding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue. flesh rends, its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we've spent with you. All hail our own Purdue. When in after years we're turning alma mater back to you, may our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're finding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue. your call once more we rally, alma mater, hear our praise. Where the Wabash spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew. Of the days we've spent with you, all hail our own Purdue. Wedded after years, we're turning alma mater back to you. May our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're binding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old.
Is it on?
No.
So, welcome back, everyone. So, for the next talk, we'll have Eugene Polzik. So, he's a professor of physics at the Niels Bohr Institute at the University of Copenhagen. He's the leader of the Quantum Optics Center, Quantop, and director of the Copenhagen Center of Biomedical Quantum Sensing. His research interests are within the quantum physics of matter and light, quantum communication, and quantum sensing. And among his notable results are the demonstration of the quantum teleportation between material objects, a quantum memory for light, generation of entanglement between distant material objects, a quantum optical interference with ultra-cold atoms, and measurements of motions and field non-restricted by the Heisenberg uncertainty. So please, Eugene, thank you.
To be here, I would like to thank Sasha and other organizers. It's my second time at such a school, and it's wonderful. So, quantum measurement in an entangled network. And the story will be, again, it's not computing, and it's kind of borderline between quantum communication and quantum sensing. And the bottom line is that if you do things right, then the Heisenberg uncertainty doesn't prevent you from sensing fields and forces as good as it gets. So there is no real limit. So this is the kind of layout of what I will be talking about. The entangled photonic link between a reference system and a sensor. And using this entangled link and engineering this reference system in the so-called negative mass regime, then you can combine those two signals and make a measurement on your sensor where both the quantum backaction of the measurement and the imprecision noise are canceled. So I'll talk about this quantum mechanics in the negative mass reference frame. I'll talk about the entanglement which is required for that. And then I will talk about a specific experiment where we're trying to show that in order to obtain the gravitational wave detection in one of those giant interferometers they use, we can offer the atomic system which will eat up the noise and hopefully improve the sensitivity even beyond the amazing sensitivity that they have now. So, what are those quantum limits of measurement of an oscillator? So, let's say we have a system and we know that there is uncertainty coming from the commutation relation, and you can renormalize it in the language of X and P, because X and P also don't commute, and therefore there is an uncertainty. Now, what does it mean? it means that when you measure x, you put the quantum back action on p. When you measure p, you put the quantum back action on x. And the same thing with the spin projections. You want to measure one projection, it inevitably puts the back action into the other one. And it's kind of easy to illustrate it in the following way. In the lab frame, when you are measuring an oscillator, you can say that in the rotating frame, x is responsible for sine omega t and p for cosine omega t. So now you have this oscillator, and at the first instance, you measure x, and you put the back action in p, and then again, and more and more. And if you're in the quantum regime, the more you measure, the more you obscure your system by the quantum measurement. And the same thing, so this is for an oscillator. For the spin, it's the same story. You measure in this kind of the spin projection in this plane, and you put the back action eventually, the bigger back action here. And yet, arbitrary small perturbations in both position and momentum and in both projections of the spin can be measured if you find the correct reference frame for the measurement. So sensing beyond quantum limit in a negative mass reference frame, there are some references here. And you need to define the trajectory of motion relative to a quantum reference. The reference should have this effective negative mass. I'll show you what it means. And then you create an entangled state between the reference frame and the system of interest. And then you publish. So for that, we need to recall what is this entanglement that I will be using in the talk. And it's always going to be the continuous variable entanglement, either x and p of an oscillator or macroscopic projections, quantum projections of a macroscopic spin. Macroscopic in the sense that we don't deal with a single spin 1/2, we deal with a big collection of spins. And by the way, everything else given the same, it's sort of obvious that you would like to have as many spins as possible to construct a quantum sensor, right? Because the quantum uncertainty of the macroscopic spin is a square root of the number of spins, and the relative uncertainty is 1 over square root. So having a million or a gazillion of spins gives you everything else given much better sensitivity. So this is why we're talking about macroscopic sensors. So a textbook example, you can have two particles, x1, p1, x2, p2, and because those operators commute, you can measure simultaneously the difference of the x's and the sum of p's. And 65 years later, then it was discussed by EPR, the criterion for the entanglement of those two systems has been derived, and it's easy to understand it because in quantization, for the standard quantization for uncorrelated systems, this variance is 1/2, this 1/2, this 1/2, and this 1/2. So the sum is 2. If it's less than 2, it turns out that the two systems are entangled. And you can obviously rewrite this with the spins, right? Simply using the spin correlation, commutation relation. Okay, so now let's say that we have two objects described by x0 and p0, one object, and x and p, the other object, and we want to measure the relative motion of those two. So we want to measure the motion of one of those objects with respect to the other one. We always make measurements with respect to something, right? So I move with respect to the table. Now here my quantum reference frame is quantum. Okay, so x0 minus x and p plus p0 can be made, as the uncertainty can be made as small as we please because we can entangle our system of interest and the reference system. Fine. So let's look what happens. The position of my system of interest with respect to the reference frame is the initial position, relative position, plus the velocities times time. Easy. Now, usually, the derivative of x is p, the derivative of x naught is p naught, and this doesn't commute with that, because you need a plus here. But now, if I all of a sudden come up with a system which has a negative mass, whatever it means, I'll show you what it means, then, oops, this plus actually, where should this plus be?
P plus P naught?
Absolutely. So my fault. The thing has moved, right? So, and this is very important, thank you very much. So it should be P plus P naught, this plus should be here. Therefore, this and this will be commuting, and then I can measure my trajectory as good as it gets. Right. Very similar things with an oscillator. If I think of an oscillator where the frequency of oscillation is effectively negative, then again, now the plus is in the correct place, because if one of those oscillators has a negative frequency, then it's minus sign, and then it minus translates into here. Good. So let me introduce one example of an oscillator with the effective negative frequency. In fact, everything is negative here. The frequency, the elasticity coefficient, and the mass. So it's a stable oscillator. So think of a collection of spins, and let's think of spin 1/2 systems, and let's orient them all along z direction up so that everybody is sitting here. Now, the uncertainty, the minimal uncertainty will be something like square root of the number of particles, right? So for uncorrelated particles, as I said, if this is n, this is square root of n. Now, what if we, and this will be in the x and p regime, so if I zoom into this area, then it's kind of almost flat, and it will be almost x and p. And so if jz is large and classical, then I can divide both sides by jz, and then I come with the renormalized x and p, which are now jx over square root of jz and jy over square root of jz. How do I get the negative mass here? Well, imagine that I generate a single collective excitation. It's super important that it's not like spin number 2 is flipped. No, it should be a superposition of one spin flip distributed over the entire ensemble. And then it will be a collective spin wave. And on the Bloch sphere, it will look like that. It will be the first Fock state of this oscillator. And obviously, the size of the first Fock state is greater than the size of the ground state. And because the sphere is curved, the first excited state has the energy which is lower than the ground state. It's also obvious from here, the energy is lowered. So this is an oscillator where I put in energy and I put in excitation and I reduce the energy. So this mathematically is equivalent to a negative mass, negative frequency oscillator. And where is the oscillator? Well, the oscillator is here. If I put it in magnetic field, it will start oscillating. Now I have an oscillator. And again, it's like a superposition of one single spin flip distributed over the entire system. So that's a negative mass oscillator. Obviously, if the spin is oriented initially in the opposite direction, then one excitation will increase the energy and will be normal positive oscillator. Excuse me. So this is one of the incarnations that we have in the lab. Believe it or not, you can do it with the large collective spin of 10 to the 10 or maybe even 10 to the 12 room temperature spins. We work with cesium atoms. At room temperature, cesium has a very reasonable density, so you can have 10 to the 12 atoms in a cubic inch vessel. And yeah, so they all run around at 200 meters per second. And then the trick here is that the walls of the cell are coated with some special coating so that spins can experience 10 to the 5 collisions without losing their quantum state. And to engineer and measure and interact with them, you use light, and light goes through. And the key point is that there is interaction without which atom information, because we measure for the time which is much longer than the transverse motion of those spins. And that becomes a system of a gazillion of atoms which are all identical with respect to the interaction and which have a very long coherence time. So that's a nice system. More of the same. So here, those atoms are sitting in this channel. This is kind of the increased picture of the channel. And you put it in the magnetic field. And then again, all those atoms move around, but they don't decohere. And you measure it and interact with them by sending light through. And it's a wonderful oscillator, because if you are playing with the ground state magnetic sublevels, then you can tune the frequency of this oscillator just with magnetic fields as good as you wish. And the Q factor, so to say, of this oscillator can be pretty amazing, because the lifetime can be up to a second, and the spin frequency can be a megahertz. So, 10 to the 6 is relatively easy. Again, we generate collective excitation, and the Q 10 to the 5, 10 to the 6 is perfect. All right. So let's try to measure something. Let's try to see that this oscillator is actually in the quantum-dominated regime. And to see that, we need to observe this quantum back action of the measurement. So we take linearly polarized light with its quantum uncertainty, like shot noise, and we send it through the spin, which is rotating like that. And what is rotating here? Well, at the very least, what is rotating is the quantum uncertainty of the spin in the orthogonal direction. But more importantly, even if you put it in the minimal uncertainty state, as you measure, because of the pileup of quantum back action, you get more and more noise. But this is a signature of the oscillator being in the quantum regime. So you can measure both cosine omega t and sine omega t projections by simply looking at this photocurrent, which will have cosine omega t and sine omega t components. You can separate them electronically, and one of them will read the z projection in the rotating frame, and the other the y. But because as they rotate and we measure, the back action piles up, then what you expect to see is actually mostly the back action noise, and this is what you see. So in this graph, the oscillation frequency is tuned to something 1.5 megahertz, and you observe a pile of quantum noise, and it's dominated by the quantum back action. The ground state noise is small. And it takes a significant amount of student hours to achieve something like that, but this is possible. Very well. So now we measure the phase operator of light, and it is the input shot noise of light in the phase, plus whatever force terms are applied to the spin, plus the back action. And note that the shot noise of the measurement and the back action are driven by different projections. And this is natural because, you know, this and that are conjugated variables, so the uncertainty of the measurement and the back action of the measurement are driven by two non-commuting variables. Now, if I take two of those ensembles and I make one of them in the negative mass configuration and the other in the positive mass configuration, and you write down this kind of commutator, so the sum of those projections and the commutator of those projections, they are equal to the sum of the jx1 and jx2, and since they are oppositely oriented, the commutator is 0, meaning that you can measure this one and that one with arbitrary accuracy, which essentially means that you can make them entangled, because if the two spins are exactly antiparallel, that they are entangled. So that's what you do, and you can create entanglement by the measurement. You simply send light through. If you only measure on one ensemble, then you will be piling the back action. But in this system, when, for instance, you send light through, the back action here and the back action here are the same back actions because the light which goes through is the same light. But the sign with which it comes into your measurement is opposite because of this opposite masses. Right, so in the top view, you see that the two spin projections are unknown, but we know that they are exactly antiparallel, or may be antiparallel. And so we have done those experiments. We have been doing those experiments for quite a while. Actually, the first one was in 2001. And we demonstrated that it works, that those two spins can be made more parallel or anti-parallel than the uncertainty of which one allows you, which basically makes it a wonderful magnetic field sensor. Because now, if one of those is subject to a field that you want to measure, then it will be affected, and you will be able, so you first measure them, you make them exactly anti-parallel by the measurement and feedback, and then you subject one of them to the signal and measure again, and now you know you can know the deviation of this spin in both x and y projections. So you can measure the uncertainty of the magnetic field or the magnetic perturbation in such a way that is not possible otherwise. You can measure two perturbations in two non-commuting variables because you are measuring with respect to the negative mass reference frame. And we demonstrated some pretty impressive femtotesla per root Hertz sensitivity with that and applied it for various things. Okay, so let's see where I am. So let's look at it in a slightly more general perspective, and let's think of now not measurements of magnetic fields, but rather of the position and the momentum of a system. And so this is a textbook example. You have a particle, you want to measure its position. What does it mean to measure the position? It means to scatter a photon from it, but a photon also has a momentum, so when they scatter, the momentum is given to the particle, and as we all know, the better you know the position, the more uncertainty you put in the momentum. So this is another example of the Stern quantum limit. If you want to know where the particle goes, you shouldn't know very well where it was before the measurement. And so you can derive from here that the motion of the particle will be the initial position plus the momentum times t over m. And since the position and the momentum obey the uncertainty principle, you can minimize the uncertainty and you find the Stern quantum limit of the measurement of motion. Now, can I employ my negative mass system to measure this motion better? Yes, I can. And I don't think I have much time to describe the optomechanics here, but let's give it a try anyway. So we want to measure the position of an oscillator. We put it inside an optical cavity. We send light through, make a standing wave. And if you have a dielectric object oscillating in a standing wave, it will modulate it. And you can measure this modulation. So if I put the input light, which is blue detuned with respect to the resonance of this cavity, then because of the motion, light will be scattered at the frequency, optical frequency minus mechanical motion, and optical frequency plus mechanical motion. It's like the acousto-optic modulator. And in this picture, obviously, this scattering will happen better because it's resonant with the cavity. So it means that I'm scattering a photon into the red sideband, which has energy lower than that one, which means that I have to somehow take this energy and put it somewhere else, and I put it in the motion. So it's A dagger, B dagger, where it's photon and it's phonon. And if I tune on the other side, I will have what's called the beam splitter Hamiltonian, and it's also called optical cooling. And if I put it in the middle, I will have the quantum non-demolition Hamiltonian. So sending light through my optomechanical system, I can make a measurement. And this measurement, of course, will also be characterized by the uncertainty of the light shot noise and the back action that I put on this system. And the back action you can think about as this light consists of photons. And those photons bombard this membrane, and they bombard it, and therefore you have a back action of this measurement, so the membrane begins to move more chaotically. And again, we achieved the quantum limited performance. So we're looking at the noise spectrum again at about 1.4 megahertz mechanical frequency of this oscillator. And we can measure it, and we can be back action limited. So the ground state noise is really very small. We're back action limited here. So now we have two systems, the atomic system here and the mechanical system here. We send light through. One of them plays the role of the negative mass oscillator, and the other one is the normal oscillator. And with this whole business logic that I just described to you, we can entangle those two. And that's what we did. And we did it because the quantum back action on one of them has the same absolute value than on the other one, but a negative sign, because one of them is a negative mass oscillator, so to say. And then you cancel the back action completely. And this was demonstrated in 2017, where we entangled the two systems. So the motion of the mechanics and the spin is synchronized better than the minimal quantum uncertainty of each of them. Obviously, you can use it for sensing as well, and there is some math describing the equivalence between the mechanical motion and the magnetic motion, but let's just skip it. Yes, so this is what we demonstrated a few years ago. This is a log scale where This is something that I've already shown you, that we can make a measurement on the membrane motion, which is dominated by the quantum back action. And we can make the measurement on the spin oscillator, which is dominated by back action. It's a log scale. And now when we put them together by moving the atomic Larmor frequency from here on top of the membrane, instead of the noise blowing up, we actually have noise cancellation. As predicted, again, this is on the log scale. So instead of the sum of those two, we have that one, and this is 6 decibel reduction of the quantum back action noise. This is a factor of 4. So it works. And it works because the quantum back action is cancelled. Now to the topic of the ongoing of most recent research. So some 6 years ago, we thought, why don't we try to use this method to help the gravitational wave observation community to measure the gravitational waves better, as if they asked us. Well, they didn't ask us. They instead followed the proposal that Jeff Kimball put together 25 years ago. And this proposal involves building a 300 meters long cavity. And they did it. They have unlimited money, or they had it with the previous administration. And we want to say that we can maybe use our little atomic spin ensemble to achieve a similar goal. So the way the gravitational wave detector works is this mirror is suspended so it can move. This mirror is suspended that it can move. The gravitational wave is a quadrupole wave, so it just unbalances the interferometer and you measure it. And after gazillions of money and long years, they managed to achieve a fantastic result where they're actually dominated by quantum noise. In the higher frequency range, they're dominated by the phase noise, which is just shot noise of the probe. In the lower frequency range, they're dominated by back action, which is radiation pressure on those mirrors. And as I just told you for 30 minutes, we, with coupling the mechanical system to the magnetic oscillator, we can suppress both here and here. And this is what we're trying to demonstrate now. So the same thing, and let's somehow put this little spin ensemble in it. It's not as small as one cell. It's, of course, the optical table, 10 by whatever, 6 feet, but it's not a 300-meter device. And the idea essentially is that we achieve the broadband quantum back action evasion because the response of the atoms in the negative mass configuration will be the same oscillatory response as the mechanical oscillator here, but will have an opposite sign. And then we can do this trick, which I already mentioned to you, that the difference of the coordinate and the difference of the momenta becomes the sum of the momenta. And then we have two commuting variables defining the motion of those mirrors with respect to the motion of the spin, which is a completely amazing story, I would say. The spin moving in the magnetic field and the mirrors moving in real time, in real space, you can still somehow couple them. So our system consists of the negative mass spin oscillator, two entangled light modes. In the previous experiment, we used one and the same beam of light so that we can have the quantum back action, which is the same on two systems, the mechanical and spin. But if we want to sell it to LIGO, we cannot use the same color because they like 106. This is their laser, and they're not going to change it for us. And cesium atoms that we use as a negative mass, they like 852 nanometers. So instead of sending one and the same beam of light, we use two entangled beams of light, one to interact with the atoms, the other to interact with the sensor. And since we don't have a sensor, then we actually kind of model the sensor. We have the atoms, we have the entangled light, and then we model the sensor response. And as usual, I don't have time for the most interesting part, but we will get to the results real quick. So this is just simple math, actually. I don't have time for it, but it's simple math, essentially saying that if I address those two systems with entangled beams of light, and one of them has a negative effective mass and the other is a normal, then I can suppress the noise in both systems. And I will get the force terms on the interferometer without any fee. So this is our simulations for LIGO done already, 6 years ago. But well, this is our team, which is apparently distorted by a gravitational wave. Anyhow, as I said, I don't have time for all that. It's essentially to demonstrate how this back action is canceled out with the two systems and how you can use it in a broadband quantum measurement. Sorry about that, sorry about that. This is a wonderful demonstration. If you tilt your head, you will actually see that we use light which is almost 10 decibel entangled between those two colors, which is a formidable effort, best in the world. La la la, la la la, la la la. This is unreadable anyhow. So here are the results. What is shown here is the broadband noise reduction below the standard quantum limit in the frequency domain stretching from a few kilohertz to like 20 kilohertz. Admittedly, this is not the 100 hertz band where current gravitational wave interferometers work, but it is orders of magnitude lower than has been demonstrated beforehand. And it's really broadband because the bandwidth is comparable to the central frequency. So we show here that by combining our negative mass oscillator and the simulated interferometer response, we can cancel all quantum noise, all and all. I mean, it's 3 decibel reduction, of course. You know, we use 6 decibel EPR entanglement and get 3 decibel sensitivity improvement. And this is done in the broadband, and other applications I don't have time to talk about. And this is the summary. So macroscopic mechanical atomic objects can be entangled and used for precision measurements of motion, force, and gravity within principle, no fundamental limits. Thank you very much.
Thank you for the talk. I might have missed that, but how do you create those collective excitations of the atom with the sign properly?
Right. So let me just use my hand. So let's say I have a 2-level atomic system, and all my atoms are here. This one is empty. I shine light, which is actually off-resonant with an atomic transition, but not too far. And as a result, I have scattering of a photon. Now, of course, I have gazillion photons scattered, but I'm looking only in the forward direction. And in the forward direction, I cannot tell which of the atoms has actually scattered a photon. And therefore, I have this collective. So if I would put a photon counter and shine this light and count photons in this arm, if I count one click, then I know that I have created one collective excitation. We have actually done this experiment and demonstrated that's true. And in those experiments, we are not looking for single excitations, but we are rather looking for scattering, which manifests entanglement of this system with another system, because another system also scatters light in the same way. Good question.
A question?
Just maybe to follow up, are your atoms in a blockade regime in this case? Are your atoms in a blockade regime in the cloud?
Blockade?
Yeah, in a sense that if only one of the atoms can be excited at the time?
No, no. So if you are familiar with parametric down conversion process, yes. Right? So think of it as parametric down. In parametric down conversion, I have a nonlinear medium, I pump it with a strong field, and I get photon pairs coming out. And if I want to write down the state of those two photonic modes, I will have 0 plus some coefficient 1, 1, plus some coefficient 2, 2, 3, 3. So photons always are generated in pairs, and this is the essence of two-mode entanglement. In my system, instead of two photonic modes, I have one photonic mode and one spin mode, or one photonic mode and one mechanical mode. But the situation is the same.
Let's thank Eugene again. And let's move to the final talk of the morning, which is by Ji Zhou. So he's a professor in the Department of Physics and Astronomy at Purdue University. His research interests include synthetic gauge fields, strongly interacting bosons and fermions, quantum non-equilibrium dynamics, and connections between few body and many body physics. And Ji Zhou received his PhD from The Ohio State University and his bachelor's degree from Tsinghua University in China. And today he'll talk about synthetic gauge fields. So please, when you're ready.
So let me first thank Sasha, David, and other organizers for the invitation and for giving me this opportunity to discuss some of our recent results that are relevant to our Quantum Science Center. Well, the study of quantum materials is a central theme in modern physics in the past many decades. Many important and interesting topological quantum matter have been discovered and studied extensively. In parallel, there have been very active research efforts to study the so-called synthetic quantum matter, ranging from large-colored atoms to superconducting circuits and nanophotonics. I believe that Vlad, Alex, and other colleagues will discuss some of these platforms in this summer school. Here, one point I want to mention is that our Quantum Science Center has very research programs on both topics, on both quantum materials and synthetic quantum matter. In particular, these two kinds of studies are not separated from each other, but actually highly entangled and correlated with each other. Say, quantum materials provide synthetic quantum matter models and open questions. Very often, our theorists would like to write down some models to explain beautiful results found by our experimental colleagues. But frankly speaking, we may not be that sure, we may not be 100% sure whether or not this is really the underlying model in a particular material, because a realistic material might be very complicated, disorders and other kinds of perturbations, okay, may be beyond the more simple models that we just wrote down. In this sense, well, synthetic quantum matter provides us with a very clean environment or a very clean platform to simulate the models themselves. Okay? And we hope that we can use synthetic quantum matter to answer some open questions provided by the quantum materials. Then, once we get some answers to some open questions in a very clean platform, then we might be able to provide quantum materials some important insights. And then new motivations say, well, in realistic materials, we might be limited by our ability to tune the parameters. But in synthetic quantum matter, typically, we can tune the parameters in a very broad range. Moreover, we might even be able to create new models using synthetic quantum matter that are not available in some materials. Then in the future, this may inspire our colleagues studying solid materials to invent more materials to study new classes of models and discover new classes of quantum phases. To really interconnect these two research topics, there is a very important ingredient, the so-called synthetic gauge fields. We all know that, well, in case we want to produce quantum Hall states and other important topological quantum matter, gauge fields are extremely important. One has to have a strong enough magnetic field to deliver certain kinds of quantum Hall states. For electrons, well, this is almost natural because electrons could naturally see electric fields and magnetic fields. Okay. But in this synthetic quantum matter, well, gauge fields are not that natural. Sometimes it might be even difficult to create gauge fields. For instance, well, atoms are charge neutral. How am I going to really create gauge fields for charge neutral atoms? So this is indeed raises, well, a bigger question mark for us. How are we going to create and manipulate synthetic gauge fields in this synthetic quantum matter? This is a central question that I want to discuss in my talk. Despite that, we may have charge neutral particles. Our experimental friends have created a variety of gauge fields for us. Well, even though we cannot just directly apply an electric field to charge neutral atoms, we can come up with some elegant schemes, such as this one, okay, which was first realized by Christopher Solomon's group at ENS. Instead of accelerating the atoms, charge neutral atoms, they actually accelerated the lattice. Okay. What they have done is extremely simple. Basically, two counter-propagating lasers could provide us with a standing wave, okay, which then provides atoms a periodical potential. Okay. Then we may have the band structure, so on and so forth. But what they have done is that they have added actual phase in time-dependent phase to one of these two counter-propagating lasers, such that the lattice itself is actually moving faster and faster. Then if we go to the co-moving frame, okay, with the lattice, then we will see that effectively there will be an electric field acting on the atoms. Okay. This is how they have observed a very clean signature for the so-called Bloch oscillation in optical lattices. Typically, in solid materials, it's difficult to observe Bloch oscillations due to disorders and also due to the rather small period of the oscillation. Okay. So this is a simple way to create an electric field. How about a magnetic field? Okay. This is a standard technique used in cold atoms to produce a magnetic field. Okay. One simply need to rotate the trap. Okay. Once we rotate the trap, if we go to the cold moving frame, immediately we will see that there will be a term that acts as if a magnetic field acting on a charge-neutral atom. Okay. This is how one may even be able to create lambda levels for charge-neutral atoms. So this is a beautiful experiment done at MIT by Wolfgang Kelly's group. Because of the rotation, atoms see an effective magnetic field, then a vortex lattice arises. Okay. This is really similar to the vortex lattice in the superconductor, but here we are talking about a vortex lattice in charge-neutral atoms. Thanks to this rotating trap, which provides us with this synthetic magnetic field, we see a beautiful vortex lattice. So these are some similar works about synthetic gauge fields in cold atoms. In recent years, many experimental groups have been using the so-called Raman coupling to produce the so-called synthetic spin orbital coupling. Okay. So this figure explains how we can create this synthetic spin orbital coupling. Well, Raman lasers could flip the so-called hyperfine spin states of atoms, and meanwhile, provide the atoms a kick. And the atoms, the internal states of the atom changes. Meanwhile, the momentum of the atom also changes. Okay. This is why the spin and the momentum are locked by these Raman lasers. And this is a typical energy spectrum produced by a synthetic spin orbital coupling. This really mimics the energy spectrum of spin orbital coupled electrons in solids. There is actually an interesting alternative means to understand this Raman coupling. This is so-called synthetic dimension. Here, these 1, 0, -1 are some internal states like hyperfine spins of atoms. Okay. But we can imagine that while this internal degree of freedom provide us with additional dimension, in addition, besides the real dimension. Okay. Say we just in this three-level system, we have a 3 by n lattice, okay? And this 3 denotes the number of lattice sites in the synthetic dimension, and n is the number of lattices in the real dimension. Okay. Then in this two-dimensional strip, we may even have a synthetic magnetic field, because this Raman coupling could really imprint phases of the lasers to the atoms. So the couplings between, the phase of the couplings between different hyperfine spin states actually depends on the position. It changes as a function of, say, x. So this x is denotes the real dimension. Okay. So the phase of these couplings between different hyperfine spin states really changes as x increases. Then, if we just focus on a single plaquet of these two-dimensional lattice formed by the combination of synthetic dimension and real dimension, we will see a net flux. And this net flux tells us that there is a synthetic magnetic field acting on the charge-neutral atoms. Okay. This is how some experimental groups could make use of this design to see the age states on the common Hall strip directly. Basically, one just needed to have the spin selective measurement, and this particular spin component simply corresponds to one age, the other spin component corresponds to the other age. Okay. One just needed to have spin selective resolution, then we will be able to see the age states directly. Another advantage of this synthetic dimension is that the boundary condition could be easily engineered. In ordinary solid materials, we just have the open boundary condition. So periodic boundary condition is something that our theorists really love when we are doing calculations. But in experiments, it's difficult to get a periodic boundary condition in the real dimension. Say how I'm going to connect this end and the other end that is far away from each other. But using the concept of the synthetic dimension, we can obtain a periodic boundary condition by just coupling these two hyperfine spin states. because now we are not talking about a real dimension, we're just talking about two different Hopf spin states. Therefore, no matter how far I put them on this plot, we can, in principle, add additional coupling so that this end and this end in the synthetic dimension is connected. This is how a few experimental groups have already realized the so-called synthetic Hall cylinder in laboratories. Not only that we have a cylindrical geometry, but also there is a finite magnetic flux penetrating the cylindrical surface. So this shall provide us with a very useful tool to study quantum Hall states on this cylindrical geometry. More than that, well, on this synthetic Hall cylinder, the band structure, single particle band structure will be very interesting. So this is the theoretical result of the band structure. Well, typically, once we're talking about a band, different bands, there must be a band gap to separate, say, S band from the P band. But here, due to a unique symmetry on this synthetic Hall cylinder, two bands have to form a group such that they intersect with each other somewhere in the momentum space. If so, one can easily conclude that if a wave packet is moving in the momentum space, after we apply a constant force acting on this wave packet, this is so, well, typically we know that one constant force shall induce a Bloch oscillation that has a finite period. But because of this intersection, then we see that if initially a wave packet started from the ground band, after one period, it does not come back to the original band. Instead, it moves to the other band. Similarly, if initially we put a wave packet on the top of the second band, after one period of the oscillation, it does not come back to the original place laser. It actually becomes a first band. In other words, the second and first band swap with each other. What does it mean? This means that we have already obtained a quantum transport on the Mobius strip. We all know that a Mobius strip is different from ordinary strip. Say, I place an object inside the Mobius strip, then after one period, once it goes along this loop, well, eventually it ends up with on the other side of the Mobius strip. This is the reason that we don't have the inner side or outer side of a Mobius strip. These two sides are connected with each other. Okay, so this is the so-called quantum transport on the Mobius strip. After we predicted this phenomenon, Yong Chen's group at Purdue soon realized this quantum transport on the Mobius strip. Here, what they measured is a momentum distribution. As we can see, well, this initial momentum distribution after one period of oscillation, in the sense that the wave vector, the momentum changes by 2 pi over d, one reciprocal lattice vector. Then we see that, well, the momentum distribution does not come back to the original one. It becomes something else. Then we have to be a bit more patient. Just we need to wait for the wave packet to finish another loop. Then the momentum distribution becomes itself. So the same results can be seen from starting from the initial state at a different band. So this confirms this picture of the quantum transport on the Mobius strip. In addition, his group has done something interesting. Well, they have added actual perturbations to open the gap by breaking the symmetry, or particular symmetry. Then now we see these two bands do not intersect with each other anymore. As such, well, we recover the ordinary Bloch oscillation. Once the wave packet finishes one loop, then it has to return to the original place. In this sense, now in the ordinary band structure, now we have obtained the quantum transport on the ordinary strip. Inside is inside and outside is outside. They are disconnected from each other. So these are some simple examples that I want to discuss to show you how we can create synthetic gauge fields for charge-neutral particles. Then the next question you might be asking is that, well, is there anything new? Okay, we can create various synthetic gauge fields in synthetic quantum matter, but what's new? Okay. This is my personal perspective. The synthetic gauge fields could provide us with new insights, new gauge fields, and new quantum phenomena. Let me start from new insight. Well, the interplay between interaction and topology is one of the most outstanding questions in the study of topological quantum matter. Okay. Then using synthetic quantum matter, we might be able to shine light onto this challenging question. Okay. In synthetic quantum matter, well, very often interactions can be controlled. Okay. Here I just provide you with example using Archie-Code atoms. Okay. The interactions between atoms can be largely tuned using various techniques. For instance, one just needs to increase the confinement. Okay? So initially, say the atoms are trapped in a very shallow trap. The interaction is very weak. But in experiments, we can impose a very strong confinement in one or multiple directions. Then the stronger the confinement is, the larger the interaction is. Using this method, okay, the interaction between atoms can be significantly enhanced. Okay. Once the interaction is large enough, regarding, say, the previously discussed quantum transport on the Mobius strip, we will see a very interesting phenomenon. Okay? The interaction could turn an ordinary strip into a Mobius strip. Okay? Why this could happen? These are some numerical simulation results. Okay? Say, if there's a band gap has opened, then without interaction, we may fear that, well, we should come back to the ordinary strip case. We just have the ordinary Bloch oscillation. Okay? But in reality, well, the sweeping rate of this condensate in the moment of space may still be finite. As such, in general, well, the dynamics won't be exactly adiabatic. Okay? In the most generic scenario, well, we have occupancy in both the upper band and the lower band. So this is what's happening in the long-interacting case. But once the interaction is strong enough, well, a condensate has well-known properties that, well, all particles prefer to stay in the condensate. Once some particles are excited outside of the condensate, there will be actual energy penalty. As such, once the interaction is strong enough, the majority of the particles will prefer to stay with each other such that these condensate simply ignore this small band gap, and all of them simply move to the upper band. Okay? So this is a numerical simulation to show that, well, the probability of the condensate to stay in the upper band really approaches 1 once the interaction is strong enough. Okay? This tells us a very important conclusion. The interaction may change the underlying topology completely. Okay. So this is certainly a relatively simple example using a condensate. Nevertheless, it provides us with some concrete results that interaction could change the underlying topology completely. Okay. So I hope that this simple example may provide useful insights for the study of quantum materials in the future. In addition to theoretical insights, well, we may be using synthetic gauge fields. We may also be able to create some highly unusual gauge fields. Okay. Here I want to discuss 2 examples, imaginary vector potential and tensor gauge fields. Well, imaginary vector potential, wait, right? I believe that many students may have this question when immediately after you see these imaginary vector potential. Well, in textbooks, we have been focused on real vector potentials all the time, magnetic field, electric field. What we are talking about are real quantities. But why we can have this imaginary vector potential? Say here, this is a famous model in the study of non-Hermitian physics, the so-called Hartonian model. Okay. This is a simple generalization of the ordinary tight body model that we are familiar with from textbook results. Okay. Here, the tunneling amplitude towards the right now is different from the tunneling amplitude towards the opposite direction. I have used two arrows with different length and width to emphasize, to highlight the asymmetry of the tunneling. This is a very simple model, but it has served as a fundamentally important tool in the current study of non-Hermitian physics. Okay. Then how to realize this non-reciprocal coupling? Well, a few groups have realized it using various techniques. But the fundamental principle is similar. Basically, one needed to require the interference between multiple pathways that connect to nearest label sites. In particular, one of these two pathways may have losses, may have dissipations. Then once you take into account the dissipation in one of these two pathways, immediately you will be able to convince yourself that the tunneling won't be symmetric. Okay? Everything really comes from this dissipation. Okay? Then once we just focus on this lower energy effective model, then we can project out this actual pathway, then we can project out these excited states that provide us with the actual pathway. Then eventually we end up with this non-reciprocal coupling. And what is really interesting is that this non-reciprocal coupling provides us with an imaginary vector potential. Why we have imaginary vector potential? Let's come back to the ordinary tight body model. The tunneling amplitudes are still the same towards opposite directions. You may notice that now these two arrows have exactly the same length and width. Okay. Nevertheless, we can add a phase to this tunneling. This is so-called Pierce substitution. In the presence of gauge fields, then the tunnelings become complex. Okay. But here, this theta, this phase is real. As such, in the continuum limit, we can write down the Schrödinger equation. Not surprisingly, we end up with a term that corresponds to a real vector potential. But here, once I make this theta imaginary, if theta becomes imaginary, then immediately we see that now these two tunneling amplitudes, the amplitude of the tunnelings towards opposite directions become different from each other. Okay? This is why we have the so-called reciprocal coupling. In other words, the non-reciprocal coupling indeed gives us an imaginary vector potential. This little I in front of this linear derivative term simply vanishes. Okay? The study of imaginary vector potential indeed is a very important topic in the so-called non-Hermitian physics. Essentially, many non-Hermitian phenomena could be traced back to this non-reciprocal coupling or equivalently imaginary vector potential. But there is another interesting perspective about the imaginary vector potential. We recently found that once we have an imaginary vector potential in the system, effectively, we have already curved the space. Well, at the beginning, we just started from a tight body model with non-reciprocal couplings. Why on earth suddenly I can claim that the space has been curved? Well, this comes from a very intrinsic property of the curved space. Say if I consider curved space, in the expression for the Schrödinger equation, the ordinary kinetic energy, the kinetic energy term that is described by this Laplace operator now needed to be replaced by the so-called Laplace Pastrami operator, in which the space-time metric inevitably enters the expression for the Schrödinger equation. Okay. For instance, if we consider a very simple hyperbolic surface whose non-element is given by this expression, from this non-element, one can work out what would be this metric tensor. Then immediately we can obtain the Schrödinger equation that describes a particle moving on the two-dimensional hyperbolic surface. One can use the standard trick by impose the periodic boundary condition in one direction. Say we set the momentum in the y direction to be 0. immediately we see that this two-dimensional Schrödinger equation reduces to the Schrödinger equation in 1D, but there's an actual piece in the Schrödinger equation. This actual piece is precisely the imaginary vector potential that we just discussed. In other words, the imaginary vector potential is provided by the finite curvature of this two-dimensional hyperbolic surface. Okay. As such, this perspective could help us to understand a wide range of interesting long-Hermitian phenomena. Okay. For instance, well, this is well known that in the Hartog-Nielsen model, once we create a wave packet, the wave packet will be pushed towards one end of this one-dimensional Hartog-Nielsen chain. It gets amplified. Okay? So this has been very strange if we just stick to the flat space perspective. But once we realize that there is an underlying curvature, say this hyperbolic surface is really described by this funnel. Okay? And then, because the circumference gradually increases once the wave packet moves towards one end, then to conserve the probability, the wave packet has to get amplified. Okay? So this means that the so-called long-Hermitian skin effect does have a very important underlying geometric origin. Okay? So this is why we feel that the imaginary vector potential will be very interesting. Okay? The other new gauge fields that the synthetic quantum matter could provide for us is the so-called tensor gauge fields. Okay? Well, typically, we are talking about the vector gauge fields for single particles in the sense that the vector potential is coupled to single particles. Say once one particle tunnel from a single particle tunnels from one lattice side to the other lattice side, it acquires additional phase. Okay. But this kind of vector gauge potential does not apply for more complicated composite particles. Say, if we have a particle pair, then this particle pair is charge neutral. Therefore, if we just apply ordinary electric field, apparently the net force and the net electric field acting on this particle pair vanishes. We won't be able to see anything interesting. Okay? On the other hand, once we can have these so-called tensor gauge fields, for instance, okay, the so-called rank 2 tensor gauge fields. These type of gauge fields are coupled not to the single particles, but a particle pair. So these could these tensor gauge fields could arise once we consider so-called correlated pair hopping. Okay. Say if two particles occupy the same lattice side, one of them could tunnel to the left, the other one could tunnel to the right. The net result will be the following. If I have a dipole like this, and due to this correlated pair hopping, this dipole could move as a confined particle pair. And then these rank 2 tensor gauge fields could couple to these dipoles. Okay. So the study of higher rank tensor gauge fields is really a very active research topic across condensed matter physics and high energy physics. Okay. There have been a lot of theoretical studies, but the question is, how are we going to realize these tensor gauge fields in laboratories? Otherwise, all the studies simply remain purely academic. Okay. So what we recently found that, well, it's actually very easy to realize at least some higher rank tensor gauge fields. For instance, we just need to put particles in a combined potential that includes a linear potential and a quadratic one. Okay. So previously, I have been focusing on this linear potential that could provide single particles the so-called Bloch oscillation, because a linear potential is really equivalent to an electric field. Here, okay, in the calculations, one can simply draw a unitary transformation to get rid of this potential energy. Okay. As a result, we will see that, well, in this correlated hopping, we will have a phase. This is a so-called rank 2 tensor gauge fields. Okay. I'm not going to discuss the calculations in detail. Here, I just want to provide you with a very simple qualitative picture. Say, once a single particle sees a quadratic potential plus a linear potential, if I consider a particle pair, then this particle pair will be able to see a linear potential, because when a particle pair tunnels, then in fact, one particle needs to move upward and the other particle needs to move downward in this potential profile. Okay? As such, well, the net energy penalty for this dipole or particle pair to move now is a derivative of the energy penalty caused by the motion of single particles. Okay? Therefore, a dipole sees a linear potential. Once a dipole sees a linear potential, we shall have the Bloch oscillation of dipoles. This is similar to the Bloch oscillation of single particles. We just need to remind ourselves that this time is not a single particle that is moving back and forth in the real space. It is a particle pair that is moving back and forth in the real space. Okay. As such, we will see that the total dipole moment remains unchanged, but the quadrupole moment changes periodically. This is really the counterpart of the ordinary Bloch oscillation, in which the total charge is not conserved, but the dipole moment is changing. Okay. Well, previously, on the previous slide, I explained to you just one type of rank 2 electric field, but there are other types of rank 2 electric field. Here, well, the electric field, well, we denote this electric field as EXZ. Previously, we have EXX, which means that the strength of the electric field changing as a function of x. EX changes as a function of x. Here, the magnitude of EX changes as a function of z. In fact, we should not feel surprised by the existence of such rank 2 tensor gauge fields. This has been studied for decades. Okay? Say, regarding the so-called extern condensate, we have particles living in one layer of materials and holes living in the other layer of materials. It's well known that there is so-called a Coulomb drag effect. Basically, if we apply electric field to only the top layer or only to the bottom layer, the mutual interactions between the particle holes could drag the particle holes in another layer. This is so-called a Coulomb drag. But indeed, the Coulomb drag could be regarded as a consequence of a rank 2 tensor gauge fields, okay? Because EXZ is finite. Okay? So this is an intuitive picture to understand this rank 2 tensor electric field underlying the Coulomb drag. So electric field is applied in the x direction, but it depends on z. So these two layers are separated from each other in the z direction. Then Ex is a function of z. As such, this layer may see a stronger electric field than the other layer. As such, the net electric field acting on this particle pair is finite. Then this finite tensor electric field shall push a pair of this particle pair to move in this plane. How much time I have? 2 minutes? Okay. Let me quickly run through the remaining slides. Okay. Well, these synthetic gauge fields could also provide us with new classes of quantum phenomena. For instance, well, recently it has been realized that bosons could condense in a very unusual way. It's not that single particles are condensing, but these dipoles are condensing. Extern condensate is just one type of dipole condensates. Okay? And this dipole condensate could also arise in the so-called dipolar Bohr-Haber model. Okay? In this dipolar Bohr-Haber model, there's a very important conservation law. The dipole moment is conserved. So this has deep connections to the so-called fracton phase of matter. Due to time constraint, I'm not going to discuss this fracton phase of matter. Instead, I want to call your attention that once we have these tensor gauge fields for these dipoles, then the conservation of dipole moment will have important implications in experiments. Okay? For instance, Well, we may have a new class of Josephson effect. Okay? You say we have two double condensates separated from each other by a barrier. Once we apply the higher rank tensor gauge fields, we will see supercurrents of dipole. This time, the net current of single particles remains exactly 0 because we just have a higher rank tensor gauge fields. And the supercurrent of dipoles really satisfy the same Josephson relation, but this time, the phase is really the phase of the dipole condensates. Okay? In other words, we may have supercurrents of dipoles in the absence of any net single particle currents. Also, we may have higher rank, one can create higher rank magnetic fields. So here I just want to provide you with a very simple example. Say, imagine that I have two layers of materials, and the magnetic field applied to these two layers are different or even along opposite directions. These provide us with a higher rank magnetic field. Then what this higher rank magnetic field could provide for us? Well, even without going to the details, we can imagine that many new phases will arise. Say we may have dipole condensates, and the dipole condensates may have vortices. Okay? This time, the vortices are not produced by single particle superfluids, but these vortices shall arise in the superfluid, vortices will arise in the superfluid of dipoles. Similarly, we may even have 10 insulators and quantum Hall states of dipoles. A whole new class of topological quantum phases will arise once we have well-controllable synthetic gauge fields. All right, I will skip the last slide. In case you are interested in more details, please go to my student, Wen Hui's poster. He will discuss on the vortex radiation, excitons will also have the so-called skin effect. Excitons will be concentrated at the edges due to the interplay between interaction and imaginary tensor gauge fields. Okay. Since I'm running out of time, let me stop here by thanking the funding agencies and all my collaborators. Thank you for your attention.
Any questions? I have one quick one. So here you're creating abelian gauge fields. Have you thought on how to do non-abelian gauge fields?
Yes. Okay. Yeah. So there are multiple ways to realize non-abelian gauge fields. Right. Well, here I just discussed a very simple setup using the one pair of Raman lasers. In principle, if one uses more pair of lasers and multiple internal degree of freedom, then indeed one can realize non-abelian gauge fields. Say, for instance, one can have two-dimensional spin-orbit coupling instead of this simple one-dimensional spin-orbit coupling. Right now, okay, on the slides, I just show you, say, the spin-orbit coupling that is written as kx times sigma x or sigma z, doesn't matter. But once we use multiple internal states and multiple lasers, we may have kx sigma x plus ky sigma y, and even more complicated spin-orbit coupling. Then there indeed, this is a very important topic. Yeah. Yeah.
Any other questions? Speaker again.
Thank you.
And it's lunchtime.
Still, we're going to break for our for lunch and our poster session. For lunch, there are vegan and vegetarian options out there. Just ask the staff if you need those. And then I just wanted to show our poster session is in a different building. It is up in our Burke Nanotechnology Center. And so for those non-Purdue folks, here's a map. We're down here in our Discover Learning Research Center. It's a very quick walk past our solar system model up into the fastest way is to go into the back door of the Bentley Bioscience Center, take an immediate left, and then walk through this breezeway into the Burke Nanotechnology Center, go down this hall, and then the poster session is in the atrium right here. So we will be back here then at 2:15, so try to leave the poster session by 5 or 10 after 2 o'clock. Any questions? All right, enjoy lunch.
All right, hello everyone. We're going to go ahead and get the afternoon session started. I'll be the moderator for this today. My name is Ryan Linehan. I'm a postdoc at Fermilab with the QSC. And I have the distinct pleasure of introducing our next few speakers. So we'll go ahead and get started with the next person. So Nick Braun earned his PhD in experimental condensed matter physics from the University of Illinois, and then joined IBM Quantum as a postdoc in 2013. He continued as a research staff member since 2015, and he's been responsible for developing and integrating quantum hardware, conducting experiments on superconducting qubits, and deploying quantum systems over the cloud. He changed roles in 2020 to start using open source software such as Qiskit to conduct experiments on quantum computing platforms, and now helps people achieve the highest performance from IBM quantum systems through hands-on guidance, videos, tutorials, documentation, and publishing peer-reviewed articles in the scientific literature with collaborators in academia and national labs. So go ahead and take it away, Nick.
All right, thank you very much. Can you hear me okay? Oh, I can hear myself now. Okay, it's a pleasure to be here back in the Quantum Science Center Summer School. It's been a few years since I came to the summer school, and I hope I have as much fun as I did last time. I'm going to cover a bunch of stuff today, so I would be happy if you were to ask questions while I was presenting, just so we all remember what page we're on. So feel free to raise your hand, or Ryan, if you want to call out people and stuff like that. You can feel free to get my attention. Yeah, so I used to be a hardware person. In 2020, I moved to the software algorithms, businessy side of things, and I started doing quantum simulation work with my friends in academia and national labs, for example, and sometimes including the Quantum Science Center. So today I'm going to give you an overview of quantum simulation, which is some of the near-term applications we expect quantum computers to be useful for, and kind of give you at least, try and give you everything you kind of need to know to get started with it, so that if you wanted to go and start doing quantum simulations on, say, maybe an IBM quantum computer, you could go home and do that tonight. Okay, so first of all, why do we care about simulating quantum systems? This is the overview. I'm going to first talk about why we want to care about simulating quantum systems, what's special about that. And then I'm going to get into the problem of mapping the physical systems that we wish to study onto an actual quantum computer. So that's kind of the meat of getting started with quantum simulations. And then in particular, we're going to go into what kinds of things that we want to observe on a quantum computer. What are the observables or energies, et cetera, that we want to measure, or dynamical observables, for example. And then we're going to talk about a new kind of algorithm that we are very interested in at IBM. It's been out kind of less than a year, and we believe that using quantum computers in conjunction with high-performance computing will yield the most promising results in the near term. So why do we like quantum simulation? Well, the first reason we like it is because Richard Feynman said it would be great if we had a quantum computer. He had many difficult physics problems involving quantum chromodynamics and very tough problems in large dimensional Hilbert spaces that kind of peter out when you try to solve them on a classical computer. So he kind of has this line saying, wouldn't it be great if I had a computer that obeyed the laws of quantum mechanics that I could then study my systems on. In particular, since then, we've identified a number of problems that we think would be very useful for realizing quantum simulations, because there's a lot of problems that are classically intractable but have large real-world implications. So for example, one of my favorite examples is something called the Haber-Bosch process. So everyone needs to eat, and where does food come from? It comes from plants. Eventually, but where do plants get their energy from? They get it from nitrogen, but the nitrogen in the air is triple bonded to itself. It's inert, so even though you're breathing 80% nitrogen right now, it's not doing anything for you. You're not getting any energy from it. So in order to become a useful energy, you need to do some sort of process called fixing it, where you can remove those triple bonds and replace them with hydrogens, and you can get something like ammonia, which then you can basically turn into fertilizer. Well, the Haber-Bosch process is something that does this. It's an industrial process that that happens at 400 degrees Celsius and 200 atmosphere and consumes about 2% of the world's energy. That is a lot of energy, and the Haber-Bosch process is actually responsible for the existence of 2/3 of humanity, because if it wasn't for this, there wouldn't be enough food for everyone. However, our friends, the cyanobacteria here, that's why there's a picture of them, they are able to fix nitrogen at ambient temperature and pressure. They're just hanging out, converting triple bonded nitrogen into useful ammonia with basically zero energy cost. And we know what does this. There's a complex called the Fumoko complex inside of it, but we don't know how it works because these transition metal molecules are very difficult to simulate classically because they have a very large Hilbert space when you have that many orbitals. So that is kind of one of the prototypical things that people who study quantum computing would love to approach a real-world problem. Another real-world problem, kind of more from where I came from, is high-temperature superconductors. So most of the superconducting qubits that we have are made out of superconductors at very low temperature. We have a microscopic theory of that. We know how they work. High-temperature superconductors were discovered in 1987, actually by IBM Zurich. These materials are actually pretty brittle, but they superconduct above the temperature of liquid nitrogen, which is 77 Kelvin. That may still sound cold, but when you realize that, liquid nitrogen is about 10 cents a liter and liquid helium is like $15 a liter, it really makes economic sense to have superconductors that you can cool to using economically viable processes, and then they can be used in things like transmission lines for lossless transmission of electricity, and say maglev trains and the like. Other interesting things specifically relevant to the Quantum Science Center is topological materials. This has been kind of a topic of focus for the Quantum Science Center to try and understand how these work, to both simulate them, to understand them, and to be able to make them in the lab so that you might be able to realize real devices. But the whole point of simulation is that once you are able to understand how something works, you're able to engineer the properties of the material better. And then, for example, other chemical catalysts we'll talk about, and this is in particular one that we were studying and have at least put on the archive in the past year. All right. Okay, so now it's time for math. I'm not going to show many equations here today, but I'm going to try and make this kind of go as simple as possible. How we think about quantum computers is basically quantum computers are very good at solving the Schrodinger equation. And symbolically, I'm just going to write the Schrodinger equation is this, as the partial derivative of the wave function is equal to the Hamiltonian times that wave function. So formally, we can write down a solution, and we're not going to explicitly solve this, but I'm going to show you how a quantum computer would solve this. But you formally can solve that differential equation by putting the Hamiltonian in the exponent and making it e to the minus iht times the initial wave function at some given time 0. And we know that this is a unitary operation because we know quantum computers can only, or quantum mechanics is only a unitary theory, so you have to actually add components to it to get non-unitary operations, but that's kind of out of the scope. We can extend these things, to open quantum systems, for example, to time-dependent Hamiltonians, where we can solve these formally with fancy integrals that look like this you might have seen in your quantum mechanics book. But for the purposes here, we're going to take things as simple as possible, and we're only going to need to think about this equation. So everything is going to be an e to the minus iht because that's what a quantum computer knows how to do. All right. Okay, so the whole idea of quantum simulation is you have something you want to study, say a high-temperature superconductor. You know maybe the state of it at some time, and you know that it evolves under some unitary evolution given by the Hamiltonian of the system under study, and you want to see what it does at some later time. So what if you had some sort of thing such as a classical simulator? A quantum computer is a general digital quantum simulator where you can actually map those onto states that you can prepare on on this simulator or quantum computer, and you can evolve it under some sort of simulation Hamiltonian, which this U prime is going to evolve your state under, and then you can make a correspondence between the system you want to study and the system you can compute, and as long as you can prepare that state at some given time and measure it at some given time, you can calculate observables and start to learn about the system. And so there's a correspondence between the system Hamiltonian that exists in nature and the simulator Hamiltonian that exists something the quantum computer can do. And for example, I'll get into more detail on this, but one kind of encoding is you can think about for fermions, so for electrons in a molecule. Electrons are not qubits. Qubits behave basically like spin 1/2 particles. They obey all the Pauli spin matrix dynamics. But what we can do is we can take those operators that represent fermions, and we can express them using some different encodings so that they can be represented on a quantum computer. And this can, in principle, be done for any type of particle. This is the Jordan-Wigner example, so this is one way of doing it, but we'll show some others. And just to give an overview of like how I think about these in general, we're going to start with a quantum circuit, which is a bunch of qubits on the y-axis as usual in an initial state. And we'll often need to prepare an initial state, so we were preparing the wave function at time t equals 0. And then we're going to do some sort of time evolution, and this is at e to the minus iht that I talk about the quantum computer being good at. And then we're going to measure some observable. Now, this could involve extra qubits. This could involve different kinds of measurements. We're going to go through some examples of that, and I think later on in the afternoon we'll hear even more about that. So let's get back to how we encode the problem. And the way we're going to talk about kind of two classes of problems first. So depending on the kinds of observables we're interested in, we could be interested in statics, such as the ground state energy of something. So you can think about a system coupled weakly to a bath as having this partition function given by the trace of e to the minus beta times the Hamiltonian, where beta is the inverse temperature, and Kb is Boltzmann's constant. Then we can write down the density matrix. So this is a kind of generalized quantum state where it's a classical probability of quantum states, and in particular the probabilities are given by these Boltzmann factors here and normalized by the partition function. So you can think about general quantum system that has classical probability or thermal properties with this density matrix. Then we can kind of think about, well, what if we want to know things, what if we want to know properties of the ground state energy or the ground state wave function? Then we can allow that kind of temperature to go to 0, and there's a number of ways we can approach it, this ground state, for example. So we can approach it adiabatically, as done in some algorithms, variationally, because we know that the ground state wave function is going to have the minimum expectation value of the Hamiltonian, because that's the ground state energy, and it can't be less than that by the variational principle. We can do imaginary time evolution. For example, if beta kind of looks like that minus IH that I showed before, and if we time evolve it, then all the high temperature states will decay to 0 before the ground state. But in particular, we're going to talk about a different variant that we're going to do. I'm actually going to do this one second, but what we're going to do is use a new sampling technique that we kind of borrowed from our friends doing classical quantum chemistry, and we've converted it over to kind of a quantum case and showed that the quantum computer can give us a reasonable degree of accuracy on some pretty large problems. In particular, what we're going to do is we're going to prepare a known state. We'll call it phi here. And then we're going to measure, basically what this means is the probability distributions of measuring all the qubits, like say from the string 0000, 00 to 1111. That's what all these X's stand for, so that's kind of just the probability of measuring each one of these bit strings. And so this probability represents a probability distribution. We'll go into detail later. This is to be in contrasted to, or let me say one more thing about statics. So statics is kind of interesting also because these ground states tend to have a lot of symmetry. There's actually very good heuristics for finding these ground states that quantum chemists have come up with for the past number of decades. So it's actually kind of we're not sure if quantum computers will actually be able to beat those classical heuristics. And I'll show you kind of where that competition is lying these days. For dynamics, this corresponds to actually measuring the state of a system as a function of time. And in particular, we can think of measuring an observable, for example. So I start with my initial state. I want to know how it behaves at some later time. Well, I can time evolve the state and then just measure that observable that I'm interested in. But alternatively, I can switch to the Heisenberg picture from the Schrodinger picture, and I can make my observables time-dependent instead of my states, in which case I have a time-dependent observable given by O of t, which is sandwiched between the e to the minus IHTs. And then you can start to use those to build dynamical correlation functions where you can look at the correlation between different observables at different times. And this is interesting because if you take the Fourier transform of this correlation function, you can get the structure factor, which corresponds directly to the kinds of things you'd measure in the lab from, say, scattering or spectroscopy or something like that. So in this way, this is kind of maybe more useful for studying actually physical systems that you can probe. Okay, so I'm going to go through examples of both of these in more detail, but first we'll go back to what do we have to do to encode the wave functions into into the quantum computer. So if you've taken quantum mechanics, you probably know that the Schrodinger equation gives you solutions or two different kinds of solutions depending on the type of particle you have, and when you have a multi-particle state. So we learned from the fact that these things are not distinguishable, that they have certain symmetries depending on what happens when you exchange the position of one and the other. And so we call wave functions bosonic if they are symmetric, meaning if I change 2, I get a plus sign in front and nothing happens to the wave function. However, if I have an antisymmetric wave function, this corresponds to a fermion where I switch the two positions and I get a minus sign in front of the wave function. And this is specifically where the Pauli exclusion principle occurs, because from this you can derive that no two indistinguishable particles can have the same wave function, because it would mean that that wave function was 0. So this is enforced by mainly common quantum chemists by taking singular particle wave functions and forming something called the permanent or the Slater determinant, depending on whether it's bosonic or fermionic. And you might have done it as an exercise in your quantum mechanics class, but it's a lot of writing down wave functions, and it's pretty tedious. So most physicists switch to something called second quantization, where instead you enforce the symmetry by the commutation relations of these annihilation and creation operators. So here, A is an annihilation operator and A dagger is a creation operator. And I have for symmetric particles, which means bosons, they have this commutation relation, which means I get an AI AJ dagger minus AJ dagger AI. That is equal to 1 only if I and J are the same. Otherwise, it's 0, which means if the operations are acting on different particles, they're going to commute with each other. Alternatively, the antisymmetry is enforced by these anti-commutation relations, where I get the CI-CJ dagger plus CJ-CI dagger is equal to sigma ij, which is just 1 if J and I are equal to each other, and 0 otherwise, which means in general, if you have these operators acting on different particles, each time you perform one, you have to get a minus sign when you each time you add one, you have to keep in mind the minus sign that comes up. And so these are the relations that are enforced here, but these are things that we can get the quantum computer to enforce as well. So this is the one we're going to prefer. We're just going to stick to second quantization. And I should also mention here is that I'm circling all these boxes. In the world of quantum simulation, there's always more than one way to do things. There's a lot of choices here, and I'm kind of choosing the simplest, most illustrative choice, but there's always more than one way. There are people that do first quantization, and you can apply that to quantum simulation as well. You'll just do things a little differently. But here we'll stick to the more textbook examples. Once we have these kinds of operators, we can start to study a zoo of quantized Hamiltonians. And so I was a condensed matter physicist back in the day, and so taking my advanced condensed matter physics classes, meaning you can get a lot of essential physics out of these problems by writing down a very simple Hamiltonian. And what I love about condensed matter physics is you can write down something that small, which explains so many phenomenon in metals and strong correlations in materials, but it's given to you by such a simple equation. So these toy model Hamiltonians actually have a lot of power in that they can show a lot of phenomenon arising just from tuning with a couple simple parameters such as T and U. So this is something called a Hubbard model. And let me tell you what this means here, basically. So T is called a hopping parameter, and it represents the rate at which particles can move. What that term Ci dagger, Cj dagger means, as long as the spins of these electrons are the same, I can destroy a particle at J and create it at I. So that represents the motion of a particle along a lattice. But it doesn't let the spin flip. It's fixed to its corresponding spin, which is given by sigma. And then what happens is if you happen to have two electrons at the same site, then you have an energy cost. So this is given by, say, some sort of Coulomb repulsion, which is indicated by this parameter U. So Ni up and Ni down, because we can't have two fermions with the same quantum state, they have to have opposite spins. But if they exist at the same site, there's going to be some energetic repulsion. So this is a popular one for condensed matter physicists. There's one for the chemists as well. This one is similar-ish in a way. in that it involves this kind of single electron hopping between molecular orbitals and the kind of dynamics between the particles, the kind of force, the electronic force between electrons in a molecule. And so this is called a singles and doubles Hamiltonian. It's kind of a prototypical example of how molecules works. Of course, you can extend it further as well. Another fun one is the Jaynes-Cummings Hamiltonian, because this is kind of the least trivial light-matter interaction in a way. So this represents the interaction of a photon with a spin. So if I imagine I have some sort of cavity that has quantized electronic modes, or in particular a resonance frequency given by omega c, then this Hamiltonian corresponds to the number of photons I have in that cavity. And then say I have a spin there, which could be a qubit, or you could think about it as an atom. That spin is pointing up or down, so it's given by its transition frequency omega a times the z Pauli matrix. And I say sigma z here, but sometimes I switch between the sigma notation and just writing z instead. And then we have a coupling between the photons, the photonic field and the spins given by this Hamiltonian and this coupling rate g. So the A dagger, A plus A dagger represents the photon field. The sigma plus plus sigma minus represents the excitations of the spins. So we basically have this isolated cavity, this isolated spin, and then the interaction between these two. And this is quite simple, but what's interesting in the kind of architecture of superconducting qubits, this is also how we kind of understand what we call the circuit quantum electrodynamics architecture. So this is kind of the first thing you learn when you are studying superconducting qubits as well, because it's a relatively simple model from which to start. But it captures a lot of the essential things that you need to know. Other kinds of models are Heisenberg models, for example. So this could be higher order spins, for example, in a lattice where you have these couplings given by J. We can have BCS-type models. So these are the kinds of Hamiltonians that describe superconductivity, where here we have the kind of hopping that we have in the Hubbard model, but we also have a superconducting gap parameter, which is given by the delta. And you'll see that something interesting about that Hamiltonian is it does not conserve fermion number, because that's a property of superconductors. And then we can have impurity models. This is something simpler where, say, you have like an insulator or a semiconductor and you have some sort of defect in the gap, for example, given by this energy epsilon d. Then you can see how many electrons are occupying that gap by the d dagger d. We can also see how that interacts with plane waves given by these epsilon k, c, ck dagger ck, the Coulomb repulsion between the defect and the electrons in the lattice, and then the Coulomb repulsion of having two electrons in the defect. So these kinds of ideas open up a large range of possibility and are often very hard to solve for very large system size classically. So now we know how to encode using, say, the Jordan-Wigner transformation. We can encode the symmetry. I guess I should have put it over here. So this kind of mapping here, for example, the Jordan-Wigner transformation means we put this string of z's here, and these z Pauli matrices have the property that they will enforce the symmetry when you map them to a quantum computer. And I didn't have an extra slide saying that, so I wanted to come back to that. But once I have these transformations, then I can just write these all these operators down in terms of Pauli matrices, basically. So you know how to go to your quantum computer, and you can write the C dagger down. It's going to be a string of z's times a sigma plus or a sigma minus. Yeah. I'm sorry, can you say that again? High-dimensional models, yeah. Oh, yeah. So the question is, so people can hear it outside, for higher dimensional models, what kind of transformations do you need to do? So there's a whole slew of different encodings, both for fermionic and bosonic and spin systems. So I believe for spins, higher order spins, you can use gray encodings or block encodings are two variants of them, but they are basically things you can write down that just make sure they preserve the symmetry of the problem. And I should also say that this is kind of an active area of exploration. People are encoding things differently all the time. So people go back to the Jordan Wigner one because it's almost 100 years old and everyone learns it in class, but there's a number of other more recent encodings that people use. And why you would want to do one encoding over another one is, for example, perhaps you could use less qubits, you could use less expensive gates. You use the C0 gates on noisy quantum systems. But all you kind of have to do is make sure whatever encoding you do follows that. I have it in the supplement. If you still want to see more, I can show you later. But there's a whole list of them, and there's more being developed. OK, so once you have this Hamiltonian here, you have these sum of terms, and you can map them to a quantum computer. So they're basically written as Pauli matrices at some point. The other problem that you have to address is that, and typically you have this Hamiltonian as a sum of local terms, at least for physical problems. But in general, those terms do not commute with each other, which means if you take e to the minus I, hi plus hj, it's not the same as the product of e to the minus iht for the individual terms. And that's because they don't commute with each other, so we have to take that into account when we're trying to map it to a quantum computer, because basically what the quantum computer knows how to do is it knows how to do e to the iht for each one of those terms, but not the sum of the Hamiltonian in general. So one thing you could do is, which is kind of the most common way to approach this, is say, well, if I just break this up into smaller and smaller steps, then each one of those terms doesn't commute with each other not that badly, in a way, such that in the limit that n goes to infinity, I have this, this is equal to equality. So you take your time you want to evolve for, and you chop it up into these dt's, and then you just do one step after another, and you can let that go, or you can make that as large as you need to. These kinds of things also have error bounds, so this would go, the error on this would go as the square of t over n. And you would just repeat this each n times, whereas this is something that can be mapped directly to a quantum computer. So you just kind of go h1, h2, blah, 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 hm. You can go to higher orders, for example. So in the second order, it's also, the higher orders are usually called Suzuki-Trotter transformations. In this way, you go t over 2n in one direction and then go back down the other direction. So you go from k equals 1 to m of this smaller time step, and then you go from m back down to 1. And that gives you an error that's cubic in the order of t over n. And you can go on and on and on, and there's all kinds of higher order trotterizations you can do that will give you less error. So you kind of repeat this kind of thing n times. There are also ones I'm not talking about, like linear combination of unitaries, for example, that have better scaling properties in terms of error, but they are kind of unwieldy to implement on today's noisy quantum hardware. So now, basically what we've done is we've taken, say, some toy model Hamiltonian, we've taken those fermionic creation annihilation operators and mapped them into Pauli strings, or Pauli operators. A Pauli string is just a tensor product of Pauli matrices. And then we put them in the Hamiltonian, and then we broke up the Hamiltonian term by term and implemented like some way like this. So term by term, we can turn this now into a quantum circuit. And let me show you a prototypical example of how this is done. So say I want to do, so I'm not doing a time evolution here, but I'm doing a rotation of theta in the 2-qubit Hilbert space, where you can map theta and t, for example, in this case. But if I have 2 qubits, I can think of a ZZ rotation as being given by a C0, then an RZ by a mount theta on one of them, and then another C0. So this kind of quantum circuit implements a 2-qubit rotation by a mount theta, two qubit rotation, a ZZ rotation by of theta in the 2-qubit Hilbert space. But this kind of basic atomic unit gives us everything we need to generate the other terms of the Hamiltonian. So in a lot of ways, like this Hamiltonian corresponds to a ZZ. That would be my Pauli string. I could evolve it for amount time t equals to theta over 2. And this would be the circuit. Now, once I have the ZZ, I know I can construct X rotations out of Z's by adding Hadamard's to either side, and I know I can construct Y rotations by adding the square root of X and square root of X dagger to either side to convert those Z rotations. So in that way, you can do something similar, where if you just want to change this from a ZZ rotation to, say, something like an XY rotation, I just add the appropriate single qubit gates on the outside. So this will give me an XY rotation in the 2-qubit Hilbert space by an amount theta. And this kind of process can be extended to any number of qubits. So if I want to do ZZZZ, 4 Z's tensor together, then that's what that circuit looks like. And this is also not unique. You can do this in different ways, but that's kind of like a prototypical atomic thing. So I have, say, some Hamiltonian. I just need to take terms like this. If there's an identity in them, I just remove the C-naughts between them. And if they're not Z's, then I just add the appropriate single qubit gates on the other side. So this is kind of how you construct each one of these terms in your trotterization. Okay, so far so good. Great. So this time evolution is how we're going, or this is how we're going to do time evolution of the system. So what I'm going to talk about next is how we think about performing measurements and the algorithms that we performed. Just going through some simple prototypical examples, and Andrew later will go into these in greater detail. But one of the ones you've probably seen in your quantum computing class is quantum phase estimation. Here, what we have is an eigenstate of U. It technically doesn't have to be an eigenstate, but let's just assume it is. And we want to know what the phase is. So we have this unitary operator we want to apply. We have this eigenstate. We know it's unitary, so the eigenstate has to be in the unit circle in the complex plane. So we can write it as e to the 2 pi I phi. And so we want to know what phi is to some precision. So what we can do is we can instantiate a register of measurement qubits or ancilla qubits, and we can prepare them in the Hadamard state, so the maximal superposition state of that register, while we prepare the eigenstate in the other register, sometimes called the simulation register. And that state corresponds to this wave function right here. It's normalized by this, and it's just a bunch of 0 plus 1s tensored with each other from the Hadamards, finally tensored with the psi plus, or psi naught, our initial state. And then what I'm going to do is I'm going to do controlled unitary evolutions, each of them to the power of 2 to the k minus 1, depending on the precision of the, on the bit precision, on the precision, on the order placement in the bit string of phi that we want to get. So each one of these controlled operations will give you one more bit of precision in your phase. And in that way, we know that the eigenvalues of these things are given by e to the 2 pi phi I. So when we actually act on those states, we can see that we get different bits of precision given by 1 times phi, 2 times phi, up to 2 to the n times phi. And when we combine those together, we actually get a phase that corresponds to phi written out bit by bit. So phi n being the most significant bit, phi naught being the least significant bit. And then we've kind of changed our, the way we wrote these so that we can do this in decimal with j equals 0 to 2 to the n minus 1. Now the problem is we can't measure the phase itself because that's something that we measure in the z basis for most quantum systems, and in that way we cannot discern the phase of these states. So what we need to do is we need to do an inverse quantum Fourier transform, and what that does is it will bring those states back down to the amplitude, and we can measure those qubits in the measurement or ancilla register, and we can get bit by bit the phase that we're looking for. So this is, I guess, been known since the late 90s. It's one of these, and phase estimation is applicable to a lot of different algorithms as well. But it's one of these kind of provably exponential speed up for quantum computers. But it's also something that's very, very difficult to do on any kind of current noisy hardware because these controlled unitary operations are very difficult. Inverse Fourier transforms are very difficult. And you're doing them to a lot of qubits. Yeah.
What's the difference between psi 0 and psi?
Psi 0 and psi. It's the same.
Oh, it's the same.
I forgot a 0. Sorry. Psi and psi 0 should be the same in this. Yeah. Yeah, thanks for pointing that out. Right, okay, so these are going to be very difficult to do anything with on any noisy kind of quantum hardware. So what we're going to want to do instead is do some kind of simplifications of this. And one of the easiest simplifications we can do is something called a Hadamard test. So instead of having a register of ancilla qubits, we're going to confine ourselves to one. And we put that single one into a superposition of 0 plus 1. We prepare a state psi or psi naught. I should be more consistent. And then what we're going to do is do a controlled time evolution on that simulation register. So do the e to the minus IHT, but it's only happening on the term where the ancilla is in the one state. And then we can do an X or Y measurement. We can't actually do an X or Y measurement, but we can rotate back into the Z basis to effectively do an X or Y measurement. And if we write the poly X and poly Ys down in this Dirac notation, then we can actually see what are the observables that we expect to get by just performing a calculation on that. And magically, we get the real and the imaginary parts, depending on whether we measure the X and the Y. So if you add those up, you can get the actual parts. So the X plus IY will be the expectation value of that unitary operator. The interesting thing here is now, if you just take that and you can do it as a function of time, you'll get some sort of curve. And you take the Fourier transform yourself, you get the same information you would have gotten from phase estimation. So in this way, you kind of, it's kind of a fundamental thing is you can apply some resources that you have, like the fact that you can do a lot of experiments and you can generate this curve, in order to keep yourself from having to do a quantum Fourier transform. Luckily for like superconducting qubits, they're very fast, so it's easy to do a lot of experiments. And you can throw that resource against the fact that it's really hard to do these large quantum Fourier transforms. There's similar kinds of observables that we can measure are like correlation functions, which is kind of a generalization of this. I start with the same kind of thing, 0 plus 1 tensored with my initial state. But here, the next thing I'm going to want to do is prepare a controlled observable. So whatever the observable that I want to measure, it's going to correspond to some, some operator that I can convert then into polystrings. So I'll do a controlled version of that. And then I'll do an uncontrolled time evolution. And then I'll control the other observable on the 0 state instead of the 1. And so I can get some expression that looks like this. And similarly, I can measure an X and Y. I get this long expression here, but everything pretty much cancels. And I get the real and imaginary parts of these correlated observable, time-correlated observables. So you can add those together to get your total time correlation. You take the Fourier transform of that, and you get your structure factor, and that tells you a lot of information. So these are things that are actually done, like today. I know Arnav has a paper on this very recently. And then perhaps the easiest one that we could possibly do is we could just time evolve the system and measure the observables that we want to. So say I want to measure some term that looks like ZXI, YZX. I just time evolve the 0 states, or whatever my initial state is, and I can measure that, and I get out my observable. And this is actually how a lot of near-term algorithms like variational quantum eigensolver work, is they're actually just measuring these observables, and they're actually typically not even employing a proper Hamiltonian time evolution, although that would be the ideal situation. So you change things based on the resources, based on the hardware error resources you can get away with. Okay, so I'm going to show some examples of this. In fact, the first example I want to give is something we call the utility experiment at IBM. This is from 2 years ago, and we'll see why we call it the utility experiment. So basically, the question is, how well can a quantum computer do at simulating itself versus having some other classical approximation simulate itself, or simulate the quantum computer? So in this state, what we did was ask the question, what is the quantum computer best at? Well, I have this 127 qubit array of heavy hexagon coupling, which is the IBM topology that we have. Each one of these qubits looks like a spin, so I could pretend this is some sort of spin dynamics problems. And these are also very relevant to our toy model Hamiltonians. And then I can kind of see how big can I go and how well can I simulate this, and then compare it and benchmark it to other kinds of approximations. And everything else has to be an approximation at this point, because at 127 qubits, that corresponds to a 2 to the 127 by 227 matrix that you have to diagonalize, which is way larger than you could fit on any classical computer. I think 50-ish is kind of the maximum there. So this is already beyond the point of brute force classical computation, and we want to look and see what are the other best techniques for solving the same problem, and how do we compare with them. So it's also kind of like a way to push the system with, see how well we can do and apply a lot of error suppression and error mitigation techniques to it, so we can try to get better results. So what does the model look like? The model looks like something we call a kicked icing model. This is basically the easiest non-trivial Hamiltonian you can simulate. So it basically looks like spins coupled to each other given by those ZZ interactions and the coupling rate J. And they're in a magnetic field given by the X polys, so a transverse magnetic field, with a strength H. And so basically what the algorithm looks like we're doing is we're just doing e to the minus IHT on all the qubits, and we're going to measure them. And we're going to try and calculate this for a number of angles, as we'll see. So we go ahead and trotterize it. In fact, we just decided to trotterize it from the outset and just do all the classical computation on the trotterized Hamiltonian as well, to even simplify it more. To make it easy for the quantum computer, we calibrated these ZZ interactions really well and used an angle that we could calibrate very well, which turns out to be minus pi over 2. So this was done, for the advantage of the quantum computer. We're trying to make it as easy for the quantum computer to do something here. And then these X, this transverse field corresponds to X rotations of single qubits. And that is the parameter that we're going to vary. We're going to let theta vary between 0 and pi over 2. And so basically, you can see these two terms of the Hamiltonian. They correspond to interleaved X rotations given by the transverse field, and ZZ interactions, I guess, are given by the controlled Z. These phase gates given by the circles, the barbells. And so that's what the circuit looks like. And then we map that onto the quantum computer, onto the topology of the quantum computer that we have that looks like this. And what we can do is we can get all those interactions done in 3 layers. So basically, it's like a graph coloring problem. We can do all the red interactions, followed by all the blue interactions, followed by all the green interactions. And each one of those sets of 3 layers corresponds to a single trotter step. And if we do enough trotter steps, we build up enough entanglement in the system that it becomes harder for, say, tensor networks to keep up with it, for example. And these circuits get incredibly large. So this is what that circuit looked like. You can't see it. You kind of have to zoom in. So we can zoom in and see that that looks like a few ZZ rotations of pi over 2. And there's a lot of them. Compared to, in the upper right, that was our VQE experiment from 2017, which had 4 qubits and depth of 2. Here we have almost 3,000 gates. We were able to get the 2-qubit gate error down to about 0.5%. In terms of thinking about these problems, the 2-qubit gate error is typically an order of magnitude higher than the single qubit error, so that's usually what you pay attention to. And we're able to push the limits of error mitigation to get competitive outcomes. And so by competitive outcomes, I mean there's a few ways we can look at this. So what we're looking at here in this case is an observable, and that observable is just the Z expectation value of qubit number 62. So this basically means I have like this lattice of spins that looks like a quantum computer. I can measure properties such as the total magnetization. I can measure single magnetization, which is, in this case, what's the magnetization of Q62. I can measure correlated observables, for example. So these are the kinds of things we can get out of the system. We're going to do everything as an expectation value of those Z's versus an angle theta. Now, in general, this is very hard to do because this is continuous, but at certain points, specifically at 0 and pi over 2, that corresponds to a Clifford circuit, which means there's an algebraic property that we can actually use to calculate exactly to very large system size. So we can do 0 and pi over 2 exactly. We know they're 1 and 0 exactly. So those are points that we know how to do, but in between, we don't exactly know what we're doing. And then kind of in this realm, what we're seeing here is these green steps right here, which is kind of the raw data that we're getting out of the quantum computer. And then we do something called error mitigation. Loosely speaking, error mitigation is I want to learn the noise properties of my system, so I run the same circuit but in different ways. In such I know that I add noise in a specific way, then I can extrapolate to the case where I have zero noise. And a lot of the error mitigation is basically used to do this. This is specifically called zero noise extrapolation, and it gives us the blue circles right here. So that's kind of the best quantum outcomes. And then we had some collaborators at Berkeley that tested some of their tensor networks, in particular a matrix product state and something called a tensor network state, I think. So tensor networks, in a way, have the same power as quantum computers in that tensor networks can represent some amount of entanglement, whereas quantum computers can represent all the possible entanglement. However, they're noisy, so you can't effectively represent all the entanglement. The entanglement that can be represented by tensor networks is given by something called the bond dimension, which is chi there. From what I know about tensor networks, for certain ones like MPS are very good at simulating one-dimensional systems, but this is a two-dimensional hexagonal system, so it doesn't do as well. So there's other kinds of two-dimensional tensor networks that can try and handle it. But what we find is that the MPS actually gets somewhat close to the quantum value, but the ISO tensor network state does not quite. And so we are in this place where we actually don't know the right answer because we can't exactly calculate it to this amount of entanglement. We did enough Trotter steps such that the light cone of Z62 covers the entire chip. So that's representing kind of all the entanglement in the system. We also did a lot of smaller light cone experiments to try and figure out how the quantum computer was doing against exact classical simulation by slicing out the qubits that didn't contribute to the entanglement. Yes, so that was the observable. They were done for a different number of times. And so then once we got that published, everyone came out and started comparing the system to their favorite tensor network. And so we were immediately inundated with papers with different research groups trying their tensor networks to try and see how theirs compared to what we got. And we had a number of, a whole slew of them, basically, to the point where we're in this area where the quantum computer gives a value which is kind of in this 20% band, especially around the angle of pi over 4, where we actually don't know which is right. We don't know which tensor network is correct. We don't know if the quantum computer is correct. They're all kind of competitive with each other. And so that's why we call this the utility paper, because we're at that point where you can show some utility in that the quantum computer can simulate itself better than a tensor network, yet this is a completely contrived problem and not useful for anything. So we don't call it advantage. And we enjoy this because it pushes the limit of our systems, and it encourages our friends in the classical tensor network area to push the limits of what they can do. And we very much foresee this being a kind of competition between tensor network methods and quantum computers going back and forth in the near term as we kind of push everything forward. So we don't see it as like a final thing that the quantum computer finally wins and goes off to the races. It's going to be, the classical approximations are going to do well also. Okay, so I'd like to do the statics experiment now, and I think I'm pretty good on time. This is going to be our more recent paper from last year. And one of the things that we have kind of come to a conclusion of is a lot of the observables, and so this is going to go back to chemistry now. A lot of the problems with chemical problems, you have these very large, spaces with a lot of Pauli operators. So that means there's a lot of individual terms in your Hamiltonian, and that means if you do an algorithm such as VQE, you have to measure each one of these millions of terms to a very large precision so that you can get a gradient out and you can converge upon the answer. And we've kind of come to the conclusion that this is not very tenable because the systems, well, one, the systems are too noisy. Two, we also have too many terms to measure, such that we calculated it would take like so many years to do these methods that I'm going to show with VQE. There's also no problem with this upcoming methods for false positives, so you don't accidentally get an energy less than you would expect to, which can happen sometimes with VQE. And there's a certain kind of So I say error mitigation, which is usually like kind of a technique for understanding noise. But in this technique, what we're actually going to do is we're going to remove noise by knowing things about the problem, such as a certain symmetry, which allows us to get rid of a lot of quantum noise and still have robust results. And then this actually scales pretty well with the, I guess, with the difficulty of the problem, something we call wave function concentration. Okay, so what is this? We call this the sample-based quantum diagonalization method. And it basically flows like this. So I have a state that I know how to prepare, and it corresponds to something approximate that I hope is near the ground state of the molecule that I'm interested in. And there's different ways of doing this. Time evolution is one of them you can do with material systems, but like I said, for chemical systems, there's too many terms in the Hamiltonian. Also for VQE, also for this technique, you can't time evolve all of them. But basically, you can prepare your states. Specifically, we were using a Hartree-Fock preparation for this. And then what I'm going to do is I'm just going to prepare that state, and I'm just going to measure all the observables. Just measure, 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 measure. And I'm going to count the probability I get for getting each bit string. So in these kinds of examples, the corresponding Jordan-Wigner transformation that I have means each term in a string I have corresponds to whether an electron is present or not. So if I have a 1, that means an electron's in that orbital. If I have a 0, that means there's no electron. So this is a kind of configuration space of the molecule we want to study. So when I measure all these kinds of things and get these noisy outputs, well, if I started with 2 electrons, this Hamiltonian doesn't let me create or destroy electrons, so I know I have to end with 2 electrons. And so that's one of the symmetries of the problem, the particle conservation, that we're going to utilize to kind of clean or mitigate the errors in the data. So from these probability of measuring all these bit strings, some of these things are going to be noisy, or some of these are going to have error, which means the tilde on the chi means they're noisy. So what I want to do is I want to clean them. So I know if I end up with only 1 electron left in my measurement, I know that's incorrect. So I do something called a configuration recovery. And I'll show how this works exactly. But I'm going to probabilistically flip those bit strings until they correspond to something physically correct. And then what I'm going to do is subsample from that set of bit strings I have. And in each one of these samplings, what I'm basically doing is I'm taking those samples and I'm projecting the large Hamiltonian onto a smaller subspace given by this h of sk. So what I'm doing is the eigenstates corresponding to these configurations that I'm measuring, I'm projecting into that less dimensional Hilbert space. And that Hilbert space is small enough dimension now that I can actually exactly diagonalize it on a supercomputer, for example. Or if it's small enough, you could do it on your laptop. Specifically, we did this on the Fugaku supercomputer in Japan, and we did this a ton of times. So I'm going to take different sets of samples from all the samples that I measured, corresponding to a certain dimension that I can exactly diagonalize. I'm going to combine those by, say, averaging over observables and looking at certain properties, and then I'm going to pass that back into the configuration recovery in some sort of, in like a variational way. But all this variational part is happening on the classical computer, so there's no error associated with that. So in some sense, for this work in particular, we're taking the outputs just from the quantum computer. Quantum computer's over. We take it over to the classical computer. So this is just a one-directional flow of work, but we can foresee how this would be used in a more iterative way with a quantum computer and a classical computer, and we're looking forward to implementing those kinds of algorithms. But specifically, I'll go into what this one was doing. So this, like I said, there's too many terms in the Hamiltonian to be able to time evolve these kinds of things. So instead, we're going to use this special chemistry ansatz, which is pretty magical, and came up with my coworker Mario Moda, which means he just knows how to create this state by essentially, these aren't really time evolutions, but they're evolved operators that will give you some sort of belief that you are going to be in the right low-dimensional subspace of your Hilbert space. So when you sample it, you're going to get the relevant information out. And we also made this local such that it maps well to our actual quantum topology. So we call it the local unitary coupled Jastrow ansatz, and that's the one we're going to prepare. And in this entire thing, we're just preparing the same state over and over again using this and measuring it just tons of times. When we map this local unitary coupled Jastrow to the quantum computer, it works quite well because we can map essentially the spin-up orbitals, that manifold, to all these qubits in the red along this line, and all the downspin qubits to the blue in another line, and they can be coupled to each other through these qubits that occur every 4 qubits, so you can get some amount of entanglement between the spin-up and down manifold. So one fun thing about the heavy hex lattice is it's kind of hard to find problems that look like it. So this is kind of a way of taking a molecule and making it work for our kinds of systems. Now, to show you kind of how this configuration recovery works, we'll just do a toy example of like 4 qubits, for example. So I'm going to prepare using that LUCJ ansatz, and I'm going to sample a bunch of times. And I'm going to get a certain number of bit strings. So say these are the 5 bit strings I got out. But I know I started with 2 electrons. So I immediately know that the bit strings in the middle are incorrect. So I flag those, and then I probabilistically flip them. This is called the configuration recovery, such that they correspond to 2 electrons in the final state. And from those recovered configurations, I'm going to subsample them. And so in this example, I'm subsampling from 3. So I have a 3-dimensional Hilbert space for each one of these configurations. Then I calculate my ensemble properties, I throw the variational principal at it, I come back and recover the configurations, for example, to get my correct answer. So mathematically, you can think of this as like, well, for one of those samples, the one in the middle that was flagged with the check mark, I can think of these being the three-dimensional Hilbert space that I have, and I'm projecting it from this starting with a 4-qubit Hilbert space, because those are that's the dimension of the bit strings I have. I'm going to project it on a 3-dimensional Hilbert space by calculating this matrix, basically, of the H's, the expectation of the H's with these eigenstates. And then I can diagonalize this exactly and get the wave functions. And then I can measure properties of those wave functions, such as energy and average occupation, and do more recovery that way. So that's how this is reducing the subspace to something that can be handled with a classical computer. And there's a certain technique for applying these in a probabilistic way, so they're kind of applied probabilistically and biased towards the raw samples. So the ones that are, the ones get pushed more towards the ones, the bit strings that look like the raw ones. There's other kinds of configuration, or there's other kinds of, a lot of checks we did to make sure that we could get the correct answer. So we could solve some of these problems, or specifically one of these problems. We could do exact diagonalization. So we can artificially add noise to it by looking at the probability of measurements in this depolarizing noise model. And we can see if we want to get below 10 Hartree, we can do so, but we need about 20% signal-to-noise ratio if we use just the raw ones, which is the yellow ones, and the yellow dots is the raw non-configuration recovery signal. But I can actually get the signal out of a very, very small signal-noise ratio. In fact, it's 2%. You could get small enough, or 2% signal-to-noise gives you small enough errors to get within that energy range. Now, of course, that energy range is a little high for stuff you might actually care about in chemistry. But this kind of analysis shows that this works. And this was for this was specifically for nitrogen dissociation. There's another thing about the properties of the wave function concentration. So you might be concerned that in the worst case scenario, my number of relevant eigenstates blows up with the problem size, which means this technique wouldn't work because it would blow up. Ideally, what you'd like to have is actually my subspace is finite, and no matter how large I make the problem size, I only have finite support of the relevant state vectors. But it turns out, instead, it's actually a manageable support, which is polynomial, which means the relative error we get does not explode when we make the problem more complicated. And so this one on the right was actually tested out for the Hubbard model, in fact. So we have a bunch of evidence that this looks good. We have a lot of reasons to believe we can get good results out of it. So then we have to compare it to the best things we can possibly do today. And so what we did here is the nitrogen dissociation. We compared the exact answer, because we can do this exactly in the black, with a bunch of different chemical techniques such as restricted Hartree-Fock, HCIs, something configuration interaction, configuration interaction singles and doubles, and coupled clustered singles and doubles. So these are, I guess, typical chemical ansatz for solving these problems classically. And we can see that the quantum does pretty well compared to the CCSD. It's just above the exact answers. And then we can compare everything exactly there, so we know we can predict how the errors scale. And so then what we actually want to do is we want to compare to the best quantum chemistry techniques available. And so generally that gets down to something called density matrix renormalization group. I'm not a quantum chemist, so I'll just say that that's the best technique for calculating these things. And because we know this is a variational problem, we know that if we get an energy lower than that predicted by DMRG, then we're actually getting a better answer because of the variational principle. So in that way, we're kind of pounding away and getting close to DMRG for certain size problems. So this smaller iron-sulfur complex, whereas the larger iron-sulfur complex we did, which I think was like 77 qubits, and quite a large problem, we're still not quite getting to the best answer predicted by the best quantum chemistry techniques, but we're getting closer and closer, and so we see a lot of hope. And this problem got, this technique has gotten quite popular, for example. So that paper came out on the archive like June of last year, and there's already been, I'd say, these 6 plus 2 more that have been put on the archive before, including some work by Travis, who I think is around here, doing defect models and using time-evolved Krylov techniques, which is kind of the, how would I say, the condensed matter version of this local unitary coupled Jastrow. And then, so one of the things we want to do is we want to make this easy. We like this technique a lot. You don't have to have a supercomputer lying around if you want to use it yourself. In fact, this will run on your laptop if the problem size is small enough. And so what we've done in Qiskit, our open source software framework for quantum computing, is we've put this technique as an add-on. So this is on GitHub. It's open source. You can download it and start using this technique right away. There's models. In the tutorial, there's models of both a spin and a molecular Hamiltonian for you to start playing with. So I encourage you to do that. And thank you for all your questions and your attention this afternoon.
All right, do we have any more questions for Nick? Any more? Okay, I have one.
All right.
So I'm definitely not a simulations guy, but I have one question. So you mentioned several slides back that you sometimes need to find problems for the model that the model fits well. How do you go about thinking about what problems, given the capabilities of the hardware and the simulation and the tools that you have? How do you go about finding new things to study and connecting with the groups that are trying to do those studies?
That's a great question. And so I kind of have an answer that I like to use if we're talking about these toy model Hamiltonians. One of the problems, say here with this Hubbard model, if we just had that first term, or even the BCS type model that I have written there, these models are actually very easily solved by classical computers using something called a Bologiabov transformation. I probably mispronounced that. Kind of basically, if you have 2 operators, and only 2, you have a quadratic Hamiltonian, and you can solve this at very large scale. So in some way, you can do a quantum simulation, and you can benchmark your quantum simulation against the classical simulation, because it happens to be in the space of easy to solve using these using this Bologiabov transformation. So you can actually benchmark your systems. But then if you add this on-site Coulomb potential term, you can't do that anymore. And so this is something that only quantum computers would be kind of good at. So recognizing these Hamiltonians, things that would extend, and then trying your model out on them, and then trying to do things much harder, that the quantum computer shouldn't care, but your classical technique breaks down. I would say almost everything that we're doing right now is trying to figure out where is the classical technique breaking down, and where's the quantum technique going to work. And I would say from talking to Javier, who's the first author of this SQD, sample-based quantum diagonalization paper, they're getting actually a lot of insight into when these problems are hard because everyone's pushing the limits from all the sides. So I would say just like you have to see like where do things break down and where you can apply each thing, I guess.
Thanks.
Thank you so much for the wonderful talk.
Thanks.
So I was wondering, like, is there any significant, or like, do you think there can be any significant quantum advantage that NISQ devices could have coupled with quantum mitigation, quantum error mitigation techniques that you guys have used over some of the classical devices? That
So
makes sense.
the question is,
Like for the particular problem of the icing model Hamiltonian you looked at.
right, so in the particular problem, the icing model, the error mitigation techniques were based on the model of the error of the quantum computer. And for the sample-based quantum diagonalization technique, the error mitigation was based on the configuration recovery, which has to do with the symmetry of the problem, which in this case is particle conservation. So these are like actually very different, and we actually don't know how well they mix. Because, yeah, I'm not sure. So typically for the SQD type things, you would use error suppression techniques, which just kind of try and suppress the noise using physics, basically. But the error mitigation is trying to like understand things about the noise, and I think it's kind of unknown how well these two can mix together. Also, the VP of Quantum has said we're going to have advantage in something by next year, so I suppose we're going to find out what it is.
All right. Oh, one more.
I'm not sure whether I have missed something important. So the model for chemistry looks very similar to the Hubbard model other than some long-range terms. Then where can I see chemical reactions?
Yeah, you're absolutely right. I think the big difference between these two, even though the Hamiltonians look the same, is the chemistry one has a lot more terms. The condensed matter Hamiltonians tend to be local interactions only, and that's not the case for chemistry. There's tends to be a lot more. But you're right, the Hamiltonian form is quite similar.
But this model does not include any reactions, which chemical reactions sometimes, well, very often may involve non-unitary equations.
Yeah. Okay, sorry. I think I might have misinterpreted the question. So the question was, we can have non-unitary interactions in chemical reactions. We can have non-unitary operations. Yes. So what I did not really talk about in this is another wide open field of doing non-unitary things. We generally call that open quantum systems, which is a quantum system interacting with a bath. And that bath has the property that when you trace it out, all the operations are unitary between everything, but you typically trace out the bath so that in effect has non-unitary operations on your quantum system. Yes, that's a very active field of study right now. So I could tell you just off the top of my head, there's one technique called quantum imaginary time evolution, where you can do this kind of non-unitary operations by approximating what it looks like with unitary operations. My colleague Mario Moda had done a lot of work on that before joining IBM. There are other ways of preparing, say, thermal states, for example. We can do that with resets, for example. We do have access to non-unitary operations such as mid-circuit measurements, resetting the qubits. There are other non-unitary things we can do. I would say for the other ones that I know of, you have to approximate the non-unitariness with the unitary operation. Yeah, so a great question. So that's just, I restricted myself to the simplest cases.
All right. I guess with that, let's thank Nick again. And we'll have a short break and come back in something like 10 or 12 minutes.
hear anything yet.
Okay,
Because
you're going to have to turn it on.
Yeah,
Okay.
actually, I think maybe. Yeah.
All right, why don't we go ahead and start moseying into our seats. We'll go ahead and get started with the next talk. So up next we'll have Andrew Stornborger. who's a multifaceted research scientist and thought leader in the areas of neuroscience, statistical data analysis, and quantum computing, with a passion for helping organizations move beyond what is present, obvious, and known. He is the Quantum Algorithms and Simulation Lead at the Quantum Science Center in Los Alamos National Laboratory. And today we'll listen to him talk to us a little bit about quantum phase estimation, how it works, and how to improve it. So, thanks.
In page, I need to update that so it doesn't sound so smug. So as Nick pointed out, the quantum phase estimation algorithm is it's a coherent quantum algorithm, the one that I'm going to be talking about. And it was first used by Peter Shor for his integer factoring algorithm. It's been used kind of as a module in many different quantum algorithms, including, for instance, the HHL algorithm. Harrow, Hasidim, and Lloyd put out an algorithm for solving linear systems of equations. And so the way I'm going to do this today is I wasn't sure, since this is a summer school, I had no idea what the range of the audience was. And so I'm going to start off by talking about, in a little bit of gory detail, about the quantum phase estimation algorithm. So I'll pretty much go over what Nick talked about in like half of one slide. On quite a few slides, I'll go into some of the math, the computations that are occurring as you run through the circuit, because I figure we're all adults here. And then I'm going to do it with the eye towards a particular place where you can improve on the algorithm. And that place, the motivation for it came from kind of standard classical signal analysis techniques that I was familiar with. And it's allowed us to take an algorithm which already is quite efficient. As Nick said, it's, because it makes use of quantum simulation, it gives you an exponential improvement in terms of resources relative, that you need to do this kind of calculation relative to classical algorithms. But it can be further improved. In fact, we're able to reduce the number of ancillas to get to a particular precision that you need to measure the energy logarithmically. So it's effectively a further exponential improvement on the algorithm. So I'll start off just saying what the classical textbook algorithm is, and then I'm going to go through the Wikipedia presentation, at least with their notation. But a quantum phase estimation is a quantum algorithm, so it's realized in a quantum circuit for estimating the phase, which means an eigenenergy of an eigenstate of a unitary quantum simulation operator. Okay, so the unitary is the exponential e to the I times energy. And the way the algorithm works is the input is the eigenstate along with a register of ancillas. So the initial state looks like this. It's a tensor product of individual zero states on the qubits, which additionally tensored with an eigenstate that you're interested in understanding some aspect of its spectrum. And the interesting thing about the algorithm is that the estimate that it outputs is binary estimate. So depending on the size of the register of ancillas, you get a binary number out. If you were to exactly find the energy, it would be a binary number, 0, 1, 1, blah, blah, blah. You would take it, convert it into a regular number, and say the energy of this state is 132 in some units. Okay? So the circuit itself looks like this. Like I said, this is from Wikipedia, so you can kind of, for people who haven't encountered this before, please go and take a look. It's got a really nice kind of discursive discussion of how it works. But the input is a bunch of zeros on the ancillas, and then this quantum state, which can be on an arbitrary number of qubits. So here I've just put M to indicate that. So the reason this superposition is up here is because each of these initial qubit eigenstates runs through a Hadamard gate, and the Hadamard on a 0 gives you an equal superposition of the 0 and 1 states. And then the tensor product of all of those states, so kind of the state at this point in the calculation, is going to be a superposition of all binary numbers from all zeros to all ones, and then everything in between. And so I want to emphasize at this point that the way to think about that is that those numbers define a lattice. We'll think of it as a lattice in time. And the coefficients define a wave function across that lattice. It's a function, right? It's a function on a lattice of size 2 to the n minus 1, starting at 0 and going up to 2 to the n minus 1. And because we have this equal superposition, it's a flat function. So it's just, constant all the way across that lattice. Down here, we have the eigenstate, and this is where the information about the energy is coming from. So the eigenstate is getting operated on by this unitary operator, u to the 2 to the 0. So just u itself, that's controlled up here onto this qubit, and then run again through this unitary, controlled up here, and so forth, all the way to u to the 2 to the n minus 1. Okay, so 1, 2, 4, 8, all the way up to whatever the number of whatever the number of samples you want to take of this time series that's defined by the unitary, as can be represented in these on the ancillas. Okay, so by the time that you're done, that your state has made it through the superposition and then the controlled U operations, at this point you have a function which is in fact, hang on one second. Okay. Sorry, I tried to make this more intelligible and then forgot that I'd put this in here. Right, so we have the equal weighting here. We have, because of the controlled unitaries, the unitaries basically kind of imprint an oscillatory, in fact, a periodic oscillatory function on the ancillas. And that function you can also think about, so I said that the superposition could be thought of as just a flat function of time. So this now is an oscillatory function of time, and I'm going to call it a sinusoid, right? I'm assuming that psi is an eigenvector, and so I just have this phase that's wrapping around, being generated and then controlled up here by by the unitary evolution in these controlled unitaries. And so here I have a function which is a sinusoid of a certain type. And then, I mean complex, but sinusoid. So the idea is to then take a Fourier transform and convert the time series into a series, into frequency, where frequency is equivalent to energy is equivalent to phase, depending on who you're talking to and how they like to express it. And so then you just measure this phase, and if things were perfect, then you would have your oscillation transformed into frequency, you'd do your measurement, and it would be a binary number which would exactly tell you what the frequency was. So the lies that are coming up in my discussion right now are because I'm using concepts that come from continuous variables, right? So if I have a sinusoid and I take a continuous function, which is a sinusoid, I take a continuous Fourier transform, it gives me a delta function out so I can exactly measure where that frequency is, okay? So let me just recap, right? So what's really happening is I start off with all zeros in the ancillas. So here I'm just talking about the ancillas, I'm neglecting the psi. And it starts off in a state which is just all zeros. Then I run it through the Hadamards, and I end up with a state which is a constant, which is 1 over the square root of 2 to the n. So just an equal superposition of all of these different possible binary states that could be that can be generated between 0 and 2 to the n minus 1. And then after the controlled unitaries, I get some sinusoid on here. It looks poor, but it really should just look like this standard sine wave. And then I perform my Fourier transform, and like I said, in this ideal situation, I get a unit probability of measuring the binary string that I can convert into a number and call it a particular energy. Okay, so now I'm going to go into, oh, great. All right, I will deal with it. Sorry, I don't know what this box is. It shouldn't be there. Shit. Pardon my French. Okay, so all right, so let me discuss what I can. So we have this initial state, which I already mentioned. It's a tensor product of the zeros on the ancillas along with the eigenstate. And when I apply the Hadamards, I get this superposition, which I can write like this. So here J is meant to, J is a binary representation of a lattice point on the ancillas, and psi is still here. And then I perform a controlled unitary operation, which I can't see, but what ends up happening is the unitary, if the corresponding ancilla that the unitary is applied to is 0, then it doesn't perform a rotation, but if it's a 1, it performs a rotation. And if you take that operation and apply it to this state, you end up with this one after the operations. So I don't act on the J, I act on the psi. That gives me my rotation from the unitary gives me this I'm calling it a rotation. It's a complex exponential. And so this is the final state before the quantum phase, quantum Fourier transform. Okay. And now I'm going to just discard the eigenstate. It hasn't changed as I've acted on it with the unitary. And so I'm just going to disregard it because everything that we want to know is on the ancillas. So one thing that I want to say, which luckily I have it down here, this theta here, which this is supposed to be pointing to, is not necessarily an integer. Just think of it as a real number. It's not necessarily, so the phase, right, this frequency that we want to measure is not necessarily on the lattice that we're performing the quantum Fourier transform. And so like I said, there's this illusion we always think in terms of continuous variables. We perform continuous quantum transforms in our head, but that's not what's happening here. And so this is a crucial technical issue that is going to allow us to improve on this algorithm. And so the part that, of course, was whited out here is this operation of a controlled unitary. That operation actually goes qubit by qubit in terms of the ancillas. So if this were an ancilla qubit and this were just a qubit state, so very simple implementation of this QPE algorithm, when I act on that with the Hadamard gate, I end up with the superposition. I act with the unitary, and the unitary only acts on psi if we have a 1 here, and that's how we end up with these phases. Geez, okay. So it's making it tough for me here. So so we have these, this is the result that I ended up with on the previous slide. I have phases that are functions. So first of all, I here is just the square root of -1, but J indicates the lattice location on, in the grid defined by the ancillas, and theta is this phase, which we want to estimate, and we don't, and it's not necessarily on the grid. So if I apply a quantum Fourier transform to this state, what ends up happening is I'm converting the J, the lattice in time, in J, to a new lattice, which I'm going to call X. And that lattice is going to be, it's probably poor notation, and you can't see it anyway, but it's going to define the possible energies or frequencies or phases that I can measure. Okay? And the final state, I don't know if any of these are going to show up well. So this is kind of upsetting. Man. Okay, so what's going to happen in this final state is the Fourier transform itself has phases, right? It's deconstructing this function of time into functions of frequency. So it's going to give me a new superposition of, so a new sum over possible frequencies. And the expression that's going to come out is going to isolate, so it's going to isolate the difference between theta and a variable, let's call it x, that is on the lattice. And so if x were exactly theta, then this expression would give me a 1. It would give me a probability, which is exactly where is exactly at the energy I want. However, if it's slightly away from the from theta, sorry, if theta is slightly away from a lattice point, then what I need to do is to define a variable. Well, I don't need to do this, but the easiest way to do it for me to explain to you why you should care about what I'm going to talk about is that the issues that show up with QPE have to do with the fact that most of the energies that you're going to measure with it are not going to be exactly on the lattice. Okay. And so what that does, if theta were on the lattice, then this delta would be 0, and I would end up with a probability of 1 here because delta would be 0. Whereas if delta is not 0, then I end up with this probability of measuring that nearest neighbor. Okay? So my actual frequency of interest was here. The nearest integer, the nearest lattice site is here. And so what ends up happening is that lattice site shares some of the probability with other nearby lattice sites. And this is the function that tells you how that sharing is done. It gives you the probability of measuring the nearest lattice site given whatever delta is. Oh, beautiful. Okay, no more white boxes. So, and so here's a key point that I need to make. That is that this probability is something that's well known from the signal analysis literature. It's called the Dirichlet kernel. And if you plot it, it looks like this. So let me point out that this looks like these are complex numbers, but you can pull out an overall phase, and this will end up looking like this function. And so what I've done here is I've plotted a number of different, I've plotted phase estimates for a number of different, for a range of numbers of ancillas, okay? So for fewer ancillas, you get this broad probability distribution, which is telling you that even if your main phase was here, sorry, even if your main frequency was here, if you're this far away from it, you're still going to measure the probability as being non-zero in a nearby ancilla. In a nearby frequency. As you increase the number of ancillas the number of ancillas in your QPE, that width gets less and less and less, okay? And so what this is telling you is that if you want to have a very accurate estimate of your frequency, you have to have many ancillas, okay? And so here I discussed a few of the implications. Okay, so here I've just, again, I'm plotting this Dirichlet function, and so it would seem that if you used many ancillas, that you'd get a very narrow peak here. But let me point out that these side lobes are fixed in amplitude. They don't go down. So you always have this not finite probability, not too small, finite probability of measuring the wrong phase when you perform this algorithm. And and like I said, you can increase the lattice, the number of ancillas to increase the size of the lattice to reduce this, but increasing the size of the lattice means you need more ancillas. So question, how many ancillas do you need? Answer, you need of order log 1 over epsilon. So if epsilon's the error that you want, invert it, take the log, and that'll tell you how many extra qubits you need, okay, to make a particular accuracy. Furthermore, you can ask the question, well, what's the worst case? This is what quantum algorithms people like to do because you can prove theorems with it. You want to ask, what's the worst case measurement probability that I can get? And with this Dirichlet kernel, the worst case measurement that I'm going to measure the frequency A when I have when I have the true phase being nearby by, say, half of the lattice point, is of order 4/10 or so. Okay, and so it's not that great. You can work with it, but it's not that great of a probability of measuring the right phase. So you'd like to improve on this. Okay. Can we improve on this? The answer is yes, and we have a paper out beating these guys over the head to actually get it submitted, and they keep finding they're theorists, they're like algorithms people, and they keep finding these little things that they have to fix. And, I'm like, the better is the enemy of the good, right? So anyway, it'll be out there soon. It is on the archive, and we prove all the relevant theorems. So, but what I want to do is tell you the different way that you need to think about this problem, again, which comes from signal analysis techniques, in order to understand how to improve, getting a high probability of measuring the nearest frequency. So, and what we're going to do is we're going to replace these Hadamards, which created this flat function, with a new state. Okay? And in the signal analysis literature, this is called a taper. And optics people, probably most of any experimentalist here would know that you always, use a Gaussian taper or window on your function in order to get good results. So this is the equivalent of using a Gaussian in the continuous context to using some new function that's going to optimize the frequency concentration that we need in order to get a good estimate. Okay, so that's the difference in this algorithm from standard QPE, and this is awesome, man. This is great. So, okay, so now I'm just going to say this in words. So what's really happening for this algorithm is QPE, it gives me I put in this superposition of, I get a constant function on the ancillas, okay, and then I'm, with the controlled unitaries, I'm imprinting this oscillatory function on that other flat function, okay? And so mathematically, what you're doing is those two functions, the one that's after what we're calling the superposition function, and then the sinusoid, are mathematically point by point multiplied. They're just two vectors, and they're point by point multiplied. And so when you take the Fourier transform of two functions that are point by point multiplied, it's equivalent to the Fourier transform of the first function, the Fourier transform of this function, which we're calling the taper, convolved with the Fourier transform of the sinusoid. Okay. So in the case where you have so in this case, the Fourier transform of this flat function, right? It's not really a flat function. It's actually zeros back to minus infinity, and then it's a bunch of delta functions, and then it's zeros to positive infinity. So the Fourier transform of that is this function, this Dirichlet kernel. And the Fourier transform of a sinusoid is a delta function. But when you take the convolution of those two, you end up having this Dirichlet function as a probability that's just shifted to where that delta function should be. So if the energy you want to measure is at 132, then the probability that you're going to get using QPE is going to be this probability shifted to 132. Okay? And so the question is, in those terms, we want to take this Fourier transform of the taper and convolve it with the Fourier transform of a delta function, which means that we have to focus on the taper, and we have to figure out how to make a taper, not a flat, delta function comb, so to speak, but something with different weights at different locations to allow us to concentrate its Fourier transform as much as possible. Okay, so good. So, okay, so here, this is what we're going to set up a cost function. So now we've taken this problem and we've turned it into a mathematical problem, with an optimization problem. I'm going to optimize a cost. The cost that I want to optimize is this. I'm going to have a taper. I want to take its Fourier transform, okay? And I want to make that Fourier transform as frequency concentrated as I can. Okay, so think about a Gaussian function, like a continuous function. I take a Gaussian, I take its Fourier transform, I get another Gaussian, right? And if I want to concentrate the Fourier transform of the Gaussian, I better make the initial Gaussian, the Gaussian in time, be, you know, be a long bump, and when I take its transform, it's going to make it a narrow peak, right? I want to do something similar, but I'm doing it for discrete function on a lattice. And so here I would have had a cost function which says I want to maximize, as a function of the taper, the integral over some bandwidth. I'm going to pick a bandwidth. I'll call it W. And the integral of the Fourier transform of the taper within that bandwidth. Okay, if that made any sense. Yeah.
Do you want to, so I guess there's a problem with the upload. Do you want to just like grab your own laptop and plug it directly in?
I could do that.
Yeah,
I
don't know how many more slides you have, but that might
I've got a few, so it can't hurt. It can't hurt. It looks like the things that are missing are things that I modified last night when I was trying to fix my notation. Okay. And I can just do this by hand if
If you have a USB, it
okay.
might take a little time.
Okay.
Yeah, oh, no, you don't have one. Okay.
Yeah, that's a standard USB. Okay, good. Okay, so this is this Fourier convolution I was talking about. This circle just means, it's called a Hadamard product, when you take two vectors and you multiply them entry by entry. And the Fourier transform of that product is equal to the convolution of the Fourier transform of the individual vectors. And so then for the standard QPE, the taper is this delta function comb. And the function, this function Q is the sinusoid. And when I do that convolution, I end up with this Dirichlet kernel. And you can see that it's shifted here because of the convolution. And so this is the cost function. I want the maximum overall possible functions phi of its Fourier transform within a given bandwidth, okay? So, okay, so that's the problem. And the question is, what kind of an optimization do we want to do? So the cost that I just wrote is measuring the average support of this Fourier transform in this bandwidth. You can also ask a question about what's the worst case, like I was complaining about the algorithms people doing to make lower bounds for theoretical purposes. And so the average case optimality can be measured. So here, excuse me, we want to optimize a Lagrangian function, right? So we're going to set up the cost as a Lagrangian function, and we'll assume that we have some flat probability that that the actual phase is within some range about a particular location. And so I won't go into the details of the cost, but if I take this and then I also have a Lagrange multiplier in order to make sure that the vector is unit length, then I end up with a kernel which, when I find its eigenvectors and eigenvalues, the largest eigenvalue is going to identify the optimal vector, okay? So the optimal taper, right? So the tapers are going to be discrete functions of time, and they'll end up, I'll use uprep in order to put them on the lattice. And so we have to find out what the eigenvectors of this kernel are. And the fact is that the eigenvectors of this kernel are called discrete prolate spheroidal sequences. They were studied at Bell Labs by a guy named David Slepian, who was a signal analyst back in the, I think, starting at least maybe 50s, 60s through the 70s. And they're, like I said, they're used a lot in signal analysis, but they hadn't been used before for quantum phase estimation. And so, and just so you know, what the optimal DPSS looks like is it looks like a lot like a Gaussian, but the tails are a little bit different because it's on a discrete, finite discrete grid. And so you can prove a couple things, and here's the exponential reduction in resources that you get. So if you remember, for standard QPE, the number of extra ancillas that you needed was of order log 1 over epsilon. And so here it's log 1 over epsilon. So practically speaking, you'll never need, irrespective of how big your QPE algorithm is, you're never going to need more than 2 ancillas, and you'll get, you know, extremely good isolation of the energy. And then you can also set up a different cost that will give you the worst case. And it's interesting, it gives you a taper that has a sinusoid. It looks like it's a sine function. So they're called a sine taper, also known in the literature, and actually also used in QPE before. This one improves by a factor of about 20 on that Dirichlet kernel that I showed. It gives you, a half as opposed to 4 over pi squared. And so here you can see how this works out. So one of the things that I wasn't emphasizing was that these DPSS functions depend on the bandwidth that you pick, that you want to concentrate them on. If you are lenient and you take a wider bandwidth, you can knock those side lobes down to like extremely small, okay? And you see that here. So on the bottom, as a function of the bandwidth, we're plotting the likelihood of measuring the wrong, the likelihood of measuring outside the bandwidth. And you can see so M here is denoting the number of ancillas. So I've kind of changed notation. But with 1 ancilla, as a function of the log of the bandwidth, you can see that already compared to these, which are standard QPE, you can do, 2 orders of magnitude better. And then with 2 ancillas, you're down. This is 10 to the minus 120, minus 120 decibels, excuse me. And so down here, you're like, 5 or 6 orders of magnitude, and then you add 2 ancillas, and you're down here at like negligible misidentification of your of the location of the eigenenergy that you're looking for. On the top, I show the worst case one, where worst case is 4 over pi squared, and as I vary the bandwidth, you can see up here is where I get to 1/2, or very close to 1/2. So I won't go too much into this, but in the paper we show that there's an efficient quantum algorithm for constructing. So these are actually what these tapers look like. in time. And the Fourier transform of that is over here. That's what it looks like in frequency or in energy. And so this is this U-prep step. It's the only modification that we make to the QPE algorithm. And so, right, so basically, we looked at how to optimize this phase estimation algorithm by using signal analysis techniques. We showed that for average case optimal accuracy, these DPSS functions, discrete prolate spheroidal sequences, they're also called Slepian functions because David Slepian was the guy who studied them a lot. Those are optimal. And then for worst case, the sine taper is optimal. And in the average case, we show that you can reduce the number of ancillas that you need by a log factor, or logarithmically. Yeah, and that's it, right? So the worst case, we do 20% better. In the average case, we do way better. And then we also provide an explicit algorithm for preparing this taper state on the ancillas. And so I apologize for the kind of weirdness of the presentation, but I'll stop there and ask for any questions.
Okay, thanks for your talk. So I have a question about QPE. So you have assumed that the qubit, say, you denoted by phi, is exactly the eigenstate of your Hamiltonian. So what if there's some perturbations? So,
That's right. So right, if you have a superposition of eigenstates, for instance, then depending on what that superposition looks like, say if it were an equal superposition, then the probability of getting one peak would be divided by the number of eigenstates and distributed. And so there would be, the statement would be, as long as you had only a polynomial number of superposed eigenstates, you would be able to, with some reasonable probability, determine them. This is the sort of case that you'd end up in with the HHL algorithm, where you have a number of eigenvalues that you're using in order to do the inversion of the linear system.
Thank you for the next talk. I think there is a trade-off between the circuit width and depth. When you add the taper function into the circuit, you essentially have the deeper circuit, right?
No. That prep circuit is okay, I mean, maybe by a few gates, but it's a very simple circuit. Okay. So, I'm being a little bit glib. It's not that, it's not just a bunch of Hadamards. Yes, but it doesn't add more than a polynomial expense to the overall circuit. It wouldn't take nearly as much time, for instance, as the quantum simulations that you have to control.
Any other questions? If not, let's thank Andrew again. And up next, we'll have Travis Humble. All right, just to introduce Travis really quickly while he gets ready there. Travis leads the center, the QSE, and serves as the primary contact for the Department of Energy. as well as leading the co-design and scientific integration and industry council coordination. Travis is a distinguished scientist at ORNL, director of the lab's Quantum Computing Institute, an associate professor with the Bredesen? I don't know how to. Bredesen Center for Interdisciplinary Research and Graduate Education at the University of Tennessee, and an associate editor for the Quantum Information Processing Journal. He received his doctorate in theoretical chemistry from the University of Oregon before coming to Oak Ridge in 2005. So whenever he's ready, he can start.
Okay. Hello, everyone. I appreciate the introduction from Ryan and all the amazing talks that we've heard today. I just want to check. You guys doing okay? I don't know if you quite understand just how much ground is being covered. And I'm really impressed, you know, both by the content, but also by the engagement. I mean, I think everybody's still sitting up straight. Nobody's hiding under the desk. So I think these are all good signs that things are going well. I am going to try not to use the entire time that was allotted, partly because I hope we can get to the panel discussion right after this and talk in a little more conversational style, but also because what I want to try to do is place in context how I see all the things that have been discussed and will be discussed later throughout the week. You probably know that it's the International Year of Quantum Science and Technology. In fact, it's over here on the PQSA flyer. 100 years ago, Erwin Schrödinger and Werner Heisenberg both published independently papers about quantum mechanics, what became to be known as quantum mechanics. This is actually the 2027 Solvay conference. I can only imagine if I were going to have a birthday party for quantum science, these are the people that I would invite to it. Right? You've got Albert Einstein, Marie Curie, Heisenberg and Schrödinger in there as well, along with a bunch of other folks. And the question, of course, at the time, if you can imagine 100 years ago, what was it that they were actually discovering? Nobody really knew. I mean, quantum mechanics and the idea of that had already been around for a little bit, but this concept of the implications that it had for everything that was going to happen for another 100 years was really far removed from their minds, is what I imagine. Now, I noticed, as I was reading through some of the literature they're giving out here, Purdue University has actually been around for 150 years, I think starting last year, which means some of the professors at Purdue were probably already digging into quantum mechanics 100 years ago. Some of the fundamental distinctions, of course, were to challenge what we were thinking about at the time. I still remember being taught that the hydrogen atom looks like the picture on the left, right? This solar system model with the proton in the center and this little Earth-like electron orbiting around it. And it probably wasn't until I took quantum mechanics that someone said, well, if the electron is negatively charged and the proton is positively charged, why don't they run into each other and collapse and all of matter everywhere disappears? And of course, it doesn't, apparently. And part of that was the quantization that occurred. And the fact that what you see on the right is a more accurate description of the modes or the atomic orbitals of an individual hydrogen atom. And it looks almost realistic, but these are actually simulations, classical simulations of what that looks like. But it took almost 80 years, and we finally have a visual representation of what the hydrogen orbital looks like, an experimental image of where we think the electron is actually located in an individual hydrogen atom. And it's not collapsing in and of itself, and matter is not being destroyed all over the universe. But rather, quantum mechanics changed our understanding of what is the structure of the universe. And of course, that gave rise to things like, how does the periodic table fill in orbitals? How do the electrons kind of pair in opposing spins? How does the proton itself get created? This led to the Standard Model and other branches of physics that I can't go into. But the emphasis is that the integration of quantum mechanics into science and technology fundamentally changed our viewpoint on what science and technology are. And of course, there's many applications of this. I think the laser is probably one of the favorites because we almost always have one of these. Okay, there it is. Available. It's integrated throughout all of our technology on Earth. Things like magnetic resonance imaging actually are based on quantum mechanical effects as well. So you can imagine health and medicine. Of course, clocks and some of the best timekeeping available based on quantum mechanical effects. So there are these revolutions that happen when we have these breakthroughs in the understanding of physics and the universe and the fundamental changes in our model as we shift from these planetary hydrogen atoms into something that's quantum mechanical, that's quantized, and has these huge implications. Now, there's other paradigm shifts that have happened in the last 100 years. And when we talk about order, we almost always have to talk about disorder as well. And you can imagine a collection of binary outcomes, things like pennies, where they can be either heads or tails. And trying to understand the order that is present within that collection of binary outcomes is something that also became important, let's say 80 years ago, when the theory of information itself became quantified and codified in a way that could lead to new technologies. And I think one of the best examples of this is the entropy function. If you have a fair coin, if I have a penny that I'm flipping, then I would say it's 50% probability it's head, 50% probability it's tails. On this diagram, the probability of the x, that is the penny being flipped, equaling to, let's say, heads, call that equal to 1, is at 50%, then I actually maximize this entropy, this disorder. And if I have an unfair coin, if I'm one extreme or the other, I can actually set up a business in Las Vegas. The emphasis, though, is that the ability to quantify information was another important breakthrough that we have gone through in the last 100 years in tandem with this breakthrough in physics and quantum mechanics itself. Now, of course, one of the people who was behind that was Claude Shannon. And if you don't know about Claude Shannon, you certainly should. He not only codified the idea of how symbols and binary information or bits can be transmitted, but also how they behave in the presence of noise and other types of effects that ultimately led to a modern theory of information. And he makes this quote. He's a story that he's recounting about John von Neumann telling him, well, you know, you should use entropy to talk about this information. Partly because it's already showing up in statistical physics where people are talking about disorder, especially in materials and atoms and molecules and these types of things. But also because nobody really knows what it means, so you'll always have the advantage in an argument. I think he's tongue-in-cheek here, but the point is it was another significant theoretical construct that changed how we think about things. And when they made the first transistor back in the 40s and 50s, that may not have seemed significant at the time. In fact, it wasn't even intended to be a transistor for the purposes of processing information. But it soon became that, where now we're making trillions of transistors in order to implement this infrastructure that we call the modern world. So the collection of information and the processing capabilities that it has now created has fundamentally changed to science and technology. So let's stop and think for a moment, because we've just talked about two radical changes in our understanding, and I say our here as the species. Quantum mechanics, which fundamentally changes how we view the universe and the physics and the interactions around us, and information theory, which fundamentally changes how we actually think about representing information and what it means to actually store and process information. There's this quote that information is inevitably physical. And I'm personally still trying to wrap my head around what this means ultimately. On one hand, I think I can reconcile the idea that all information, the sound of my voice, the visuals on the screen, the neurons processing, some of us may have more of those than others, but still, the point is there's a physical format in which all this information has been encoded, and that storage and processing is necessarily physical. On the flip side, all of that physics then can also be represented by information as well. And the choice of physics that I use can make a very significant difference in the type of information that gets stored and processed. And in this case, quantum physics and quantum mechanics is a fundamental departure from the way that we've thought about information previously. And that's the big idea, right? That's the thing that we're trying to take advantage of now. It's gone through many different name changes. It's currently called quantum science, but the truth is it's that intersection of these two big ideas, that quantum mechanics, a more fundamental nature of description of the universe, and information theory, which tries to capture the fact that information is inevitably physical. Those two things coming together makes a big difference for everything. Now, that doesn't actually pay the bills. So in my day job, this is the types of problems where we try to apply this paradigm. If you think about the sun, you think about the high energy physics reactions that happen in there, fusion and fission and other types of collisions, we know that's fundamentally described by quantum mechanical processes. We were talking earlier, someone mentioned power distribution, and I should tell you that from the Department of Energy's perspective, the current transmission system is incredibly inefficient in that there's a lot of loss in electricity, partly due to resistance in the wires that the electricity is being transmitted through, but also through other inefficient couplings and just not necessarily having the best location of sources and generators for that energy. But if we could come up with materials like superconducting materials that could be deployed in room temperature settings, we could have ways of ensuring a more efficient energy distribution infrastructure. Now, of course, our best understanding is that those superconducting materials themselves are intimately tied to quantum mechanics and strongly correlated electrons that are behaving in a way that's very difficult to capture with conventional modeling and simulation techniques. And then, of course, where are we going to store that energy? Whether it comes from the sun or the power distribution system, the ability to create batteries that can actually capture and transmit mechanical energy into chemical energy and back and forth become an important part of our bigger global energy distribution system. And we know that catalysts play an important role in that, as well as they do in many different chemical reactions. Nick was talking earlier about nitrogenase and the creation of ammonia from nitrogen fixation process that actually fundamentally depends on a catalyst as well. So modeling high energy chemical reactions is another place where we expect quantum mechanics and this intersection with our understanding of those reactions to be an important topic. Now, I think you've got to have seen this quote or some version of it 4 or 5 times today, but it's really important because it's adopting this paradigm shift about how we capture the effects of quantum mechanics within our modern paradigm of information, how we're shifting that now to say, well, let's talk about quantum science as a platform upon which to enable this discovery and innovation. So we want to make a simulation of nature, whether it's the sun or superconductors or chemical reactions or whatever thing you can think of. But doing that on a quantum platform is not easy for many reasons, and you've heard a lot of those. But the ability of controlling information takes us beyond that paradigm of the fact that quantum mechanics itself is information. But being able to control that in a way that we can actually get out useful information from the calculation or simulation or communication or sensor or whatever it might be is a challenge that we're currently addressing. Now, there's many different technologies out there. I just threw in this slide as a snapshot of a few that fundamentally come down to how well can we control the behavior of individual particles of matter, whether they be electrons or photons or individual atoms. Of course, all of these are kind of thinking about current technologies. There are many others under development. There are many not included on this slide. But the emphasis is that they're now getting to a point where we have realizations, instantiations of how we can merge quantum physics and information theory together, how we can create a platform where we can simulate nature using quantum mechanics and get back results that are actually meaningful and useful. Now, I'm not going to tell you that all of these systems are ready to go today. They're still undergoing development. In fact, one of the marvelous things about the field is if you wait 6 months, there'll be a new system that pops up that greatly improves upon what we thought was possible. We can track that. You can look at over the last 2 decades at the number of qubits, the fundamental elements of these systems, and how there's been a steady growth in the number that are available across many different technologies. And these different colored dots actually correspond to different commercial systems that we have received publicly released data upon. And then on the right-hand side of the big red line that says today are the projections where we expect to see the number of physical qubits to go in the next decade. And you can see that it's on based on the axis that we're getting to many thousands of qubits. And that's great. I mean, it's a lot of growth and a lot of progress. It still motivates this question of, though, well, how many qubits do you need before you can do something that you can't do in this classical paradigm? When does the quantum paradigm actually pay off? And this crossover point in which classical computation and quantum computation can cross each other still remains to be demonstrated. We've had some really good examples of where those lines appear very close to each other. But finding a good application, whether it's simulating high energy physics or materials or chemistry, that can outperform some of our best techniques today with a, let's say, unquestionable margin, is something that has not yet been demonstrated, except under, I would say, rather specialized circumstances. Now, it's happening, though. We're getting closer. There's been some very nice results that have come out from different laboratories doing a special case, again, one of those specific circumstances of a random circuit sampling problem. And that in itself is fine. You know, being at Oak Ridge National Lab, we have one of the world's fastest supercomputers. We often get used as the high bar for measuring the performance of a quantum system to how well a classical computer can solve the same problem, this random circuit sampling. And what you're seeing in the plot here is over the last 5 years, a measure of the hardness that was projected for the classical computer to have to solve in order to keep up with the quantum device. And there's kind of been a back and forth competition between Google and this USTC group in China, where they're each really focused on this random circuit problem. When you plot out the data, this all just came out very recently, it looks like it's increasing at a doubly exponential rate. So that's a log of hardness, and hardness here is a measure of the amount of time that we think the supercomputer would take to match the quantum computer solution. Well, doubly exponential is fast, by the way, and it indicates that at least we're approaching this intersection between the classical and the quantum performance much more quickly than I think will be easy to recognize, in the sense that if it's moving this quickly, it can happen and be well beyond, with an unquestionable margin of performance, before we even really realize that it happened. Now, random circuit sampling is probably not the most widespread application, but it is a litmus test for what's going on within this area. John gave some really nice examples earlier about problems that we think are important and estimates about the resources that we think will be necessary for them to be solved on quantum computers. And you can see whether we're talking about quantum dynamics, the collisions or chemical reactions, the quantum chemistry problem, think of that as kind of electronic structure type things, and then of course factoring, which is again a niche application. We're many orders away from where we are at the moment. We've probably got a few thousand qubits at best available, and my shaky math on the amount of logical operations that we can do in some of these systems has us around 1 second. We can debate about the math tonight at the bar. But my point is, we're moving doubly exponentially fast towards these crossover points, and we're starting here. I can't tell you when we're going to suddenly shoot off into another region of this plot, but I know we are. And I know that when that happens, we need to be ready. We need to be able to think about how we would use these types of systems in order to solve these important problems. Now, 5 years ago, the United States established what they call the National Quantum Initiative. It's based on a document called the National Strategic Overview for Quantum Information Science. If you really like reading dry policy documents, I encourage you to look it up. But it made some really strong statements, and one of those was an emphasis on science. I mean, like, this was unequivocally the single most important priority for the United States, and it continues to be the leading strategy document. And for us, that meant establishing within the Department of Energy these 5 National Quantum Information Science Research Centers, and QSC is one of those. Probably the best one, but I won't argue that now. The other 4 are just as good. We all tackle slightly different problems. I would say what we specialize in particular is the intersection between quantum materials research and quantum computing research, which necessarily has created these new types of devices and sensors that provide us information between those 2 worlds. Now, the others, we can talk more about that later, but what I would emphasize is that developing new materials, creating these kind of new pathways to quantum technologies continues to be an important part of what we do. Understanding how to control and modify those systems, whether they're condensed matter or atomic, molecular, or optical, that sort of chip-level engineering is a priority. The creation of the infrastructure necessary to test and evaluate these technologies, both in their prototype form, but also when they become commercially available. And then finally, the integration of all of that into our infrastructure. This is an important part of how we're going to ultimately adapt quantum science and technology into scientific discovery. You know, are we going to use quantum accelerated high performance computing systems? Are we going to have quantum enhanced sensors at our neutron sources? All of these kind of questions depend on how well we actually push the technology forward and what we can do with it. Okay, so for the QSC in particular, all of these ideas emphasize what I would consider sort of 3 big priorities. One is we want to accelerate secure, energy-efficient computing. Quantum computing may get us faster time to solution. It may reduce the amount of instructions my algorithms require or the speed at which my gates occur. It may also lower the energy it takes to solve these same types of problems. So what I see as important is to emphasize that we can continue to push forward on the technology development so that in the long term, as we build out these big systems, we can actually address these hard problems. One of those is predicting new physical and chemical behaviors. And that includes simulating the types of materials that we've been talking about, both in terms of their, let's call them exotic properties, but also in terms of the physics of their devices. How will they behave at large scales? How will they become useful in these integrated infrastructure? And then finally, I love this one, but to enable exploration of the previously unmeasurable. And you heard Eugene talk about earlier, there are these noise floors that effectively limit the perception that we have as classical beings. And until we become capable of harnessing these quantum mechanical effects, that stands as like a veil that we can't get past. So being able to enable that, to go beyond this shot noise limit actually becomes an important part of what not just the Quantum Science Center does, but what all 5 of the National Quantum Information Science Research Centers do. Okay, I've actually probably got like 20 more slides, but I think I'm going to stop because, one, I think it's been a good conversation so far, and I think we have maybe a panel discussion coming up that might be a better venue for this, but I'm also happy to take any questions just based on what's been said right now. Thank you very much.
Any questions for Travis?
Good choice.
We'll just make sure to grill him during the panel. So.
Sounds good.
All right, let's thank Travis again, and we'll go ahead and get the panelists up here. So could everyone who volunteered to be on the panel come on up here? We'll move some chairs out to the front. I think that'll be better. And I think Vea was gonna MC. I do not see her. It's a minute to get ready.
Alrighty, thank you everybody. And thank you to our amazing speakers today for introducing us to so many beautiful concepts in quantum computing and quantum information science. My name is Via Iyer. I am going to be the moderator for today's panel session, and we are going to be talking about how do we assemble a full quantum computer? So this is taking the stack from all the way at the lowest level in terms of hardware implementation, all the way to the highest level of the stuff that we see on, let's say, Qiskit or any other available stack that we normally interact with. So I guess I can start off the conversation with a quick question for our panelists. We can start with you, John. What parts of the quantum computing stack do you think most need improvement for any given technology or architecture at the moment?
Yeah, it's a good question. So I'll maybe preface my answer with saying that my background and familiarity is with kind of the solid state qubits. So obviously the Majorana approach that I was talking about earlier, and that has some overlap with spin qubits and superconducting qubits. I'd say at the moment, all three of those systems, probably if I had a magic wand, the thing I would fix first would be like the materials and fabrication processes. There are kind of different reasons for different qubit technologies, but whether it's disorder that limits your topological gap or makes all of your quantum dots and your spin qubits different, oxides or the residues that give you RF loss, and so on. I think those are one of the big challenges right now. The APS March meeting that was just last month, I think this was a pretty common theme across a lot of the presentations, that a lot of the companies that are scaling up their fabrication efforts, for instance, are really focusing on how can we make our wafers more consistent? How can you screen enough of them in large enough volumes that you can pick out these really small signals of what is it in my in my fabrication recipe that really impacts the qubit performance. So.
Yes, absolutely. Andrew?
So my point of view comes from quantum algorithms. A lot of what the algorithms group at Los Alamos does is to work on hardware that we have available one way or another, maybe on an API in the cloud somewhere, or via co-design with a vendor. And the thing that we've been seeing most recently over the past few years is the increase in the fidelities, the improvement in the fidelities of the vendors that are out there. I think, you know, probably trapped ions and neutral atoms were first, but everything is coming along. And because of that, from the algorithmic side, I think that we need to focus more as, you know, as things move forward on early fault tolerance algorithms. So if in the talk that I gave today, I talked about a way of improving the QPE algorithm. Why? To reduce resources. The way that we're going to get quantum computing to work is to, you know, improve from the bottom up, the engineering and the hardware materials side, and improve from the top down. And so, you know, I think an important focus is early fault tolerant error correction methods, you know, partial fault tolerance, ways to make this kind of nascent fault tolerance more possible, so that as the hardware gets better, the algorithms are there in order to make it happen sooner.
I have one. So I'm arguably the least quantum computing person on this panel. So what I hear and what I am trying to follow is more of the quantum simulation work in my lab, beyond and besides what I was talking about today. So what I hear from good theorists like Ignacio Chirac and company is that it would be invaluable if a system of, you know, 10 by 10 qubits or 20 by 20 qubits with engineered interactions along certain directions, or, you know, long-range interactions, like maybe everybody to everybody, they'll be incredibly difficult to calculate, and that can be a great resource for benchmarking theoretical calculations. And this doesn't have to be fault tolerant. In fact, significant level of intolerance or tolerance can be actually acceptable.
That's a great question, and I have two answers. So I think the first one I'll say is we showed at APS that we can get coherence time in superconducting qubits up to like a couple milliseconds, which is quite high. We're quite happy with that. But the challenge is then integrating these so that you can put them on a chip with hundreds of qubits and have them all have such high coherence times. So I think the integration is a challenge, but it's kind of an engineering challenge and can be worked out. Another thing I'd like to bring up is that the classical control electronics and software that sits above the stack has been, like, I don't think it's always appreciated how important it is, because it has, you know, been a problem that we've addressed over the past couple of years, where we run into problems with performance. We hit the limits of like classical control bottlenecks. What most people don't think of is, you know, when I was an experimentalist in the lab, most of my time was waiting for waveforms to load. The experiments were like over in seconds, but the waveform loading took maybe half a minute or something like that. So the whole transfer of bandwidth and measurement data and results has been like greatly improved in both Qiskit and the like back-end control electronics and back-end software. And I think that's essential for both error correction And it's going to be essential for bringing any kind of like useful algorithms to fruition, because we've already kind of reduced by an order of magnitude the amount of time it takes to do the kinds of experiments I was talking about earlier. So I like to appreciate that.
Of course, thank you. So we can stop here for a second and address any questions that the crowd might have regarding how we can put an entire quantum computer together. Yeah, Ryan?
Yeah, so TLSs I think are kind of a pain for all the solid state systems. For the topological qubits specifically, you know, some of the same likely TLSs that cause problems for the superconducting qubits also are an issue for us, just in the sense that you know, that decreases your Q factors of your resonators that you use for readout, and that decreases your overall sensitivity to the qubit state. And you know, as you're really trying to push the envelope on your SNR and everything, you know, that does matter. The other thing in the topological qubits are also, you know, similarly for the spin qubits, is that any two-level systems that charge can hop on or off will then contribute to charge noise, which you know, which those qubits are sensitive to by one means or another. And so that's, you know, anything you can do to reduce those will also make your qubits, you know, easier to control, easier to read out, and ultimately more scalable. Yep.
Any other questions? Okay, great. So, oh, I'm so sorry. Go ahead. I can bring the mic over to you, actually.
My question goes to Nick. You talked about room temperature superconductivity. Has there been any experiment in IBM on that, like on superconductors that can function above 77 degrees Kelvin? Sorry, 77 Kelvin?
Yeah, so the high temperature superconductors were first discovered at the our Zurich lab. That was in the 80s, and you know, I'm not aware of too much current research on high temperature superconductivity, but what's been interesting is these materials that were discovered, they're usually called cuprates. They're kind of like ceramics, like think of your coffee cup, and they have these layers of copper oxide that we think have strong correlations, which cause them to be very difficult to figure out how they work. But since then, I'd say in the past 10 or 15 years, there's been a slew of new higher temperature superconducting systems that are not of that form, but do superconduct above 77K. And a lot of people, I think, don't know how they work. So like, say, like iron, like superconductors that have iron in them, that was like almost a, superconductors and magnets don't like each other, so no one ever thought there'd be an iron-based superconductors, but now people have found examples of it. So there's a lot of weird and new materials that have been discovered in the past 10, 15 years. And so it'd be interesting to, you know, think about if you could tailor anything to room temperature, then that would be, of course, worth a lot of...
That would be a breakthrough, sure.
It would be a breakthrough, yes. Thanks.
Thank you so much. Great. So a question that I had actually is building off of Travis's presentation about how every 6 months a new system shows up and really changes the entire landscape of quantum computing. So as a researcher, how do you judge how these systems hold up against everything that exists right now? Because Andrew, you mentioned, you know, quantum error correction. There are also, you know, hardness mechanisms you can use. So how do you stay on top of these new and upcoming architectures, and what kind of benchmarking mechanisms like error correction can you use to quantitatively monitor them?
So I guess there are kind of a few different reactions I have to that question. So one is obviously it's important to benchmark things and to, you know, get data on on what the current technologies are capable of. But more to the point, I want to address, so Travis talked about this double exponential increase this was first seen by, well, it was first talked about by Nielsen and Chuang, that every qubit that you add to a simulation doubles the size of the Hilbert space. And then industrially speaking, if you're following a Moore's law, then that means you get a double exponential increase in the kind of size of your computational space. And when Google was going towards their supremacy work back a few years ago now, they measured this, so I think Hartmut Nevin has talked about people coming to him and saying we need more computational power in order to simulate the system, and it was going up as a double exponential. So the point to my mind about a double exponential has to do with technological risk. So, because if you plot a double exponential, it doesn't look like an exponential, it looks like a wall, right? You go along and then all of a sudden it's up in the stratosphere. And so, so what that means from the competitive point of view is that you're either there on the curve or you're behind. So you're either ahead or you're not even in competition. And yeah, so that's your kind of question brought that to my mind. The other response that I have is, so there are two of us on this panel that are old enough to have seen the growth of quantum. My first paper was in 1999, on high-order Trotter methods, and in NMR, quantum computers didn't exist back then, nor did trapped ion, nor did superconducting, nor did photonic, and through the course of my career, I've seen these all happen, and that affects the way I look towards the future, because once you've been through, 2 or 3 or 4 rounds of exponential improvements, when you look, for instance, we're going through a renewal now for the QSC, and when you look 5 years down the line to what might be there, you have to think in exponential terms. And it's something that a lot of people don't do, particularly younger people who maybe are halfway through an exponential increase, which is almost linear, and so maybe I'll leave my comment there, but that's how I think of the development of technology.
Well, just, to add to this point, back in 2006, in Europe, I was made a coordinator of the project that was supposed to put together the groups which are working on quantum information at that time. And I counted, on 2.5 hands the number of groups that were working in the subject at that time, 2 in Denmark, 4 in Germany, 3 in France, 1 in Italy. And it was easy. And since then, you know what happened. This was the double exponential growth, that's for sure. So good news that I believe it's too big to fall nowadays. And another good news is that I think we should be ready for the unknown things to come. And they will come.
Absolutely. Nick?
I guess I should say that we have a roadmap that you can look at online and tells you where we think we're going to be in a number of years. But yeah, I also agree. There's so much new stuff. I mean, I've just been in the field for 12 years, and I've seen so much growth. So maybe I'll be older and jaded one day. Thanks.
For sure. John?
Yeah, it's a good question. In terms of trying to stay on top of things and yeah, how do you kind of benchmark the systems against each other? I can offer maybe a very practical comment that just as someone working in a very focused research program, it's essentially impossible to stay on top of everything yourself. I think talking to people who are experts, in different areas, is probably the best way. There just aren't enough hours in the day to read all the papers on the archive. And maybe in terms of the benchmarking, I guess maybe what's sort of implicit in that question is sort of how do you determine what technology is sort of in the lead or has the most promise, and I kind of expect that as these systems start getting bigger and bigger, the way to benchmark them will get more and more of a judgment call in the sense that you can always talk about what's the coherence time or what's my logical qubits error rate, but then you also have to start thinking about things like, okay, what's the logical qubit clock rate, and how big is this system? What's sort of the slope that any given technology is on, and so that's maybe not a really definite answer, but maybe just food for thought of how the field is sort of evolving over time.
Yeah, of course. Thank you. Any questions from the audience regarding how we can benchmark future systems? Alrighty. If not, I can move on to the next one, and I think Eugene, you'd be a great person to answer this. So we all know how absolutely interdisciplinary quantum computing is, quantum sciences at the moment. You can be from any field of STEM or the natural sciences, and you can find a spot in quantum computing for sure. So how can I, for example, in one very specific subfield, be able to meaningfully contribute to other subfields given this interdisciplinary nature?
Well, it's an excellent question, and kind of the usual answer is that a couple of professors get together over a glass of wine or beer and decide, oh gosh, why don't we get together, because like I know something, you know something, and let's apply for funding. And this is usually the way to go. So what? I mean, I can give one specific answer from my personal experience. And again, it started from an initiative of a mathematician whom I happen to know, and who knows a quantum chemist. And we started talking about putting together a program for quantum simulation. And then we started calling funding agencies, and one of them was crazy enough to give us money. And this is how it went about. So I would say that, of course, it definitely depends on the stage of your career. And, if you're a postdoc, you have limited capabilities. If you're a young faculty, then you have many more capabilities. And seriously, you just should look out and find the colleagues at different sub-areas and reach out. I don't think I can say more.
Of course, Nick?
So the funny thing is, I was just reading about this, and I forget who some scientist I was reading about, and he was talking about the most, fruitful places for research are where subfields intersect. So, I think I completely agree with Eugene, is that you learn from your friends and you apply for grants, but you're kind of pushing the boundaries in both of what you're looking at. So it kind of, it depends on exactly what you're doing. But some of the best people, I know in, productive in quantum computing and from industry are people that have like a physics and a computer science background. That's just two subfields that are, pretty far away from each other, but then when you're at the cutting edge, that's where they're intersecting. And so you're pushing the boundary in this kind of new direction.
Right, absolutely.
Thanks.
John?
Yeah, so I think maybe my advice, you know, for somebody sort of early in career would be, you know, who's trying to kind of break into the field more or establish themselves would be, you know, to network as much as possible. And if you have opportunities, for instance, for internships or kind of visiting researcher type positions, I think those are quite valuable in terms of kind of just broadening, you know, your horizons, your skill set. And, you know, as the saying goes, it's not what you know, but who you know. I think that, you know, that helps a lot, whether you're trying to go into industry or a postdoc or whatnot. You know, having those connections that, you know, if somebody's sifting through resumes and they can put a name to a face, I think that's, you know, practically speaking, sort of a leg up. So.
Yeah, so I can speak from the national lab point of view. And, you know, one of the things that is pretty much ubiquitous in the DOE laboratory system is that we work in teams. It's very seldom does somebody just go and have an idea and put out a paper, or, you know, it's usually somebody might have an inkling of an idea and, you know, understand enough to know what they don't know, and go and, you know, find a group of people to work on a problem. And you know, in my opinion, it's a very efficient way of doing things, because you have, you know, experts that are available that you can, you know, bounce off of and work with, and it's a good way to do things. So all of, you know, I think really we're all saying the same thing in a different language depending on our position, you know, or our location, our institution.
So basically, anybody can find a place in this field, and I think that's good enough motivation for everybody that, you know, this is feasible for everyone to at least make some kind of meaningful contribution in, which is always great motivation for all of us. So back to the audience. Any questions regarding this topic? Even if it's not regarding the topic, all questions are more than welcome.
Sorry, maybe can I just say?
Yeah, of course, please.
So, you know, look in the mirror and ask yourself, how many senior scientists have I spoken to during this 3 days conference? And if the answer is less than 10, then you're not doing your job. So, you know, come ask questions, make silly statements. You're at the stage of your career when you can make as many mistakes as you wish. So.
Of course, thank you so much. So yeah, back to the audience. Yeah, Ryan? I can run the mic over to you, excuse me.
I guess along this theme as well, I'm curious to know for each of you, if there was a period of time in your career where you felt like you made a choice to make a big switch, or even a small switch from like one subfield to another. How did that go? Like, what was the switch? How did that go? What did you struggle with? Like, you know, some of us are thinking about this, right? Like, some of us, I come from particle physics, and I'm entering this new field, and I'm learning a lot. But I'm kind of curious how that went for all of you, if that happened, and just to know more.
I can almost guarantee you that I have the most such situations in my life. Well, maybe not. But so I studied computational linguistics in college, and then I worked in industry for 2 years in computers, and then I went back to studied physics, did cosmology, did 2 postdocs in cosmology, and then I got married, and my wife had a position at Columbia So I moved to New York, and I switched to neuroscience, worked with an applied mathematician in neuroscience 4 years, and went to University of Georgia, where I worked in neuroscience. I worked in signal analysis for multivariate neuroscience data, and then went to UC Davis and continued that, but I was starting to do a little bit more quantum computing there as well, and I was switching from neuroscience to neuromorphic computing. And then I went to Los Alamos for my neuromorphic computing chops. But the managers there realized that I had done quantum, and so they hooked me up with those guys, and now that's taken off because there's more funding for quantum than neuromorphic. And let me tell you, every single one of those switches is an exponential learning curve. And for a scientist, it's the best thing. You know, I mean, every time I switch, I'm like, oh my God, I cannot believe that I'm switching. And then I'm like, this is fascinating. When I switched to data analysis, you know, coming from cosmology, where, you know, everything was like equations on blackboards, and I was like, you gotta be kidding me. You know, my advisor came in, he's like, look, Andrew, you know, I know that you like doing these differential equations, but I'd really prefer that you be working on data analysis. And I'm like, oh, geez. But I did, and of course, it's fascinating, right? And there's all sorts, you know, quantum information science, right? Just information science generally. So it can be brutal, you know, it can be brutal, but it can be, you know, freeing in terms of opening your mind up to do different things.
Okay, so admittedly, there are theorists and there are experimentalists, right? So let's take this into consideration. But I'm an experimentalist. I used to be a theorist when I was a kid, and then for certain reasons, actually it helps tremendously to be a theorist. Okay, my PhD was in a very mundane optical physics, atomic physics, and then I was forced into theory for the reasons which were beyond my reach. And then when I came back to the experimental physics, that was amazingly effective. But then within the experimental field, I would say that my kind of jumps, or I wouldn't say I abandoned. So I started working with cold atoms. I gave up at cold atoms because there were too many people working with cold atoms. Then I started working with room temperature ensembles, which were just an amazing ride and still continues. And then if I know something about the way to describe atomic ensembles, then when quantum optomechanics appeared, I thought, oh boy, this is easy. It's the same thing, and let's just get those membranes and keep working. So I would say that, I think it's maybe obvious, but if you get to learn a couple of experimental platforms, and if you choose them right, and you find the way to combine them that nobody has found before you, then you know your tenure track is going well.
Of course, thank you. Any other questions? Okay, well, we can move on to a slightly lighter topic, and we can start with Nick for this. So clearly, quantum computing is useful, but terms and conditions apply, right? Like, it's useful in certain parts for experimentalists, and for it to be actually relevant in our lives, it needs what we call in computer science a killer application. So what would you describe as the closest, most achievable killer application for quantum computing to actually have relevance in our lives?
That's a great question. I would say quantum simulation, because that's you know, what I presented on today. But when I think about the most immediate applications of quantum computing, I always ask the question of what maps most naturally to the quantum computer. And spins map the easiest to quantum computers. Fermions map kind of the next best to quantum computers. And then, you know, maybe I'd start to say some optimizations actually use some of those Hamiltonian techniques, and they tend to map well to quantum computers. But I kind of put them in that order. So maybe condensed matter, physics simulations, and chemistry optimization, perhaps.
Absolutely.
But I could be wrong.
John?
Yeah, I think my answer would probably be pretty similar there. That you know, starting out with simulations, and then yeah, probably the biggest you know, killer app would be in the chemistry simulations. That you can start, you know, like the nitrogen fixation problem is, I think, a good example of one that has, you know, really serious societal implications. If somebody can, you know, reduce the world's energy consumption by, you know, a couple of %, that's a huge deal. So.
I guess, so one answer I give to that question is that I think in terms of making good use of quantum information, it's already being made use of in places like LIGO and quantum sensing. And I think that there's room on the quantum sensing side to be thinking, you know, trying to more creatively use quantum information in few qubit systems. From the algorithmic point of view, I think we all agree that, I mean, quantum simulation, you know, even if you could do a quantum simulation on, say, 100 qubits, logical or physical, you know, it's pushing the limits. So, you know, I think that's more or less where we stand.
And also, again, in this wonderful spirit of combining things that few people have combined so far, think of a quantum repeater. So a functional quantum repeater would need many quantum processes at each node for error correction and stuff like that. It doesn't have to be huge nodes. So you combine the transmission with conversion of the flying qubits into the stationary and operational qubits. And here you go. And this, well, I absolutely, you know, agree with the simulation part. That's certainly true. Yeah.
Absolutely. Anything to add from the audience? Yeah, of course. Excuse me.
I don't know how relevant this question is, but I'm wondering about like the job market for like new graduating students who are looking forward for jobs in quantum science or anything related to quantum. What do you think about the job market now, and if you have any advice for like people who are about to graduate, like to get a good job in quantum? Thank you.
What I experience and my colleagues who are group and center leaders experience is like, you know, any good person of your age which pops up in the job market has a lot of options and a lot of offers. So at this point, I think you guys just have to make wise choices. It's not that there is a lack of options. So, you know, if you have exhausted the options in this country, look in Europe.
Yeah, I hear they're doing stuff in Australia as well.
I bet if Travis was here, he'd tell you that he puts together a newsletter every Sunday that lists all the open jobs in quantum computing. But he's not here, so I'll say it. Other things I would say is I have friends who have been on the job market, and my friends who are professors have students who have been on the job market. One thing that's been true maybe the past 2 or 3 years is that a lot of the jobs are tailored with someone in mind, like with a very specific set of skills, like they want you working on day one, knowing what you're doing. Well, like, I am a converted condensed matter physicist. They took a flyer on me and made me a postdoc. So that maybe isn't happening so much anymore. It changes all the time, though. It's like market conditions.
Yeah, I think one thing that comes up a lot, I think, in kind of the nationwide studies about how do we advance quantum as an industry and all, is that everybody raises that, hey, the workforce is not big enough. So I think that there are a lot of jobs and opportunities out there, and as somebody who's trying to hire new folks with expertise in these areas, usually it's the folks with good backgrounds, they get multiple offers. So as a hiring manager, you have to move quick, I think, on the good candidates. So I think that's good news for all of you. Yeah, that's probably the best thing I can say.
Of course, thank you. Actually, shifting the conversation back towards more, I guess, quantum computing theory. John, in your presentation, you show the diagram of like the applications of like quantum chemistry and like the number of qubits that you would need to actually get to realize that, and the relative time that these algorithms would also take. So you said that you needed about a million qubits at the least to be useful. So what's the trade-off between finding new technology, like like topological superconductivity, to fill like the holes that already existing technology has, versus honing in and improving what we already have? Because there's obviously like constraints on resources, on money. So where do new scientists focus? Do we put our focus on finding new things or improving what we already have, or is it like a ratio of the two?
No, that's a good question. So I guess my thought on this would be that the companies, somewhat by necessity, have to pick one thing and really focus on it. And there's a tremendous amount of engineering that goes in, to these. You could pick in the last 6 months any big paper from any company. Like, there's large groups of people focusing on really specific problems to make these demonstrations come together. And so there's just not, even though Microsoft, IBM, Google, like these big tech companies have large teams, you can't do just everything out there. I think on the flip side, the academic groups, especially for newer ones, are going to have an increasingly hard time competing directly with a company that has 200 permanent researchers working on something. But they have a lot of opportunities for pursuing these kind of niche experiments to say, hey, what's this new high-risk idea that if it pays off, could make these qubits dramatically more robust or simpler to operate, and so on. So yeah, I think it maybe depends a little bit kind of what setting you're in, where to focus.
Absolutely. Andrew?
I think from the National Lab point of view, again, we try to identify things that may be different from what what industry is doing, exactly for the reasons that John was just talking about, that they're going to be committed to their roadmap, but that still could provide a need moving into the future. So I mean, and I think, so maybe one anecdote was I remember being at a conference where, and I forget the gentleman's name, but he was the person at Intel who was the head of their so-called roadmap. And he gave us a talk on how Intel managed that. And what he said in the end was really that there was no roadmap. What they did was they identified roadblocks. And of course, this was by the time that they already knew that transistors were the way to go, and they were, working to keep Moore's Law working. But effectively, Moore's Law was a sequence of technologies. It was not, just you set it and forget it kind of thing. And he said what they did industrially was to make sure they had all the best technology that they could be working with, and they identified the roadblocks, and then they farmed them out to academia. They had a group of people or a group of laboratories who, understood how to attack problems that industry might have. Once they were solved on a small scale, then they'd be brought into industry, and it wouldn't surprise me if that sort of thing were to happen, particularly for some of the quantum computing technologies that are seen to, take off, start scaling, and so forth.
So, like I said in the beginning of this discussion, I'm not the best expert in quantum computing, and yet we have a group, and we work on ultra-cold atoms coupled to two-dimensional waveguides. And we proudly believe that there are not too many groups in the world who are doing that and who know things that we know. And we believe that we may be able to have, 10 by 10 all connected in different ways, two-level systems, which can perform simulations that maybe will be difficult to do calculations upon. And, correct me if I'm wrong. If somebody already has done that, then maybe we should stop.
I think from the perspective of industry is probably if you want to build a quantum computer, you probably need to be in industry, or maybe you're a government or something like that. Academia serves a very important function because you can think about all the novel ideas that come out of, one professor trying out something and having his grad student work on a project, and she makes a new gate or a new coupler or a new whatever. And you're allowed to try out things like on a much smaller scale because you don't have a roadmap, and you can you are the fab. I was the fab when I was a grad student. You just get in there and make it, see what happens. And I used to work with, we used to have hardware collaborations, and it was much, much easier for me at IBM to have some parts made at like NIST or Princeton and then sent to me, versus like me spending months taping out and developing a mask and stuff like that and simulating every little part of it when I just needed to try something out. So there's kind of like, I think, roles for everyone to fill in this whole ecosystem, and I think it's great that we can work together.
Definitely, thank you. We have about 5-ish minutes left of our panel, so are there any other questions from the audience? I should mention that this is the best time to get these questions out. Yeah. Sorry, could you pass that back?
Hi, just following up with what Andrew said, what roadblocks do you anticipate for, addressed to all of the panelists, for each of your individual platforms? If you anticipate any.
So we had a workshop last year on quantum algorithms where, from which we're assembling white papers that are all on roadblocks. And I think everyone sees them from their point of view. If you asked me about roadblocks, I'd say it's, making more efficient quantum algorithms, and, and everybody's going to talk from where they sit. So I'm not really sure I have a very good answer at this point. Potentially the experimentalists might have a better idea.
Maybe I can add my thoughts on this one. So I think in the short term, as I already mentioned earlier, for the solid state qubits, I think the sort of fabrication of materials, uniformity and quality and everything is a big challenge. In the longer term, though, I think those issues will get solved, and then the biggest challenges will be the integration of these systems as they get very, very, very complicated. If you're talking about hundreds of thousands or millions of qubits, these are just very large systems with a lot of moving parts to them that, I think similar to how you can have sort of emergent phenomena in In nature, very complicated engineering systems also wind up with kind of their own challenges that maybe you didn't foresee, when you were working on 10 qubits, but when you're working on 100,000, you kind of encounter new challenges that kind of constrain your solution space.
I'll offer a slightly different alternative. So I think just something you've seen in, IBM, we have a roadmap, and we decided that, kind of our basic unit or basic module of quantum chip is going to be around 150 qubits, because that works for us for a number of fabrication and integration reasons and such. And I think that is different for every kind of modality that you can look at. So for example, ions have a little trouble scaling up so much, like in a trap you can't fit more than 30-ish or so without having heating problems. But if you look at cold neutral atoms, you can have thousands or something like that. And so the way that these modules will kind of integrate with each other, I think is going to be something kind of interesting that we're seeing coming up, and especially how that plays into quantum error correction, for example. I'm not saying that's a roadblock, I'm just saying that's going to be something of general interest, I think, to everyone, no matter what kind of hardware they work on.
Great, thank you. Any last minute questions to close out the panel? Yeah, one sec.
Hi, I was wondering what kind of metrics or features do you guys look at in research when you want to gauge sort of the impact or the validity of a paper you're reading in your respective fields?
I think it's damn easy. Number of Nature Science papers, number of citations to your work, conferences to which you are invited to give talks. And then all that combined will bring in funding. And funding will bring more research and more invitations. And then you live happily ever after.
Okay, great. Well, with that, I think we'll close out the panel for today. Thank you once again to our amazing speakers for coming out, taking the time out to answer all of our questions. And I'll just hand it off to Ryan to close out today. Thanks a lot, guys.
All right, thanks everyone for listening and asking great questions. This is the end of the day, but we also have food plans. You'll see that on the agenda. I forget the exact name of the, say what? Lafayette Brewery, thank you. So we're gonna go there and have food there.